Hey, how's everyone doing this morning? I need to update that to say mini term 2021. But who's having a good morning in the chat? I see Tyler here. I see Deacon here. I see Sam, Layla, Jesse, Haley, Zach, Kylie. Who else is here right now? Biggest thing I can say right now about being successful in the class is being here. We're about to do some chapter 15 and chapter 16 today. We only have 4 more chapters left, and then we're done. Good morning, Sarah. Good to see you here. We have 4 chapters left. I can't believe it. Now the background freezes. I was trying to do that when I was doing some other videos this week, and I was like, really? Background, you're just going to do that? Trash William says, what's trash? The 4 chapters left, the class being over? No! So I do want to point out, last night, especially with the assignments, my hair is just being all crazy. It's always crazy. Last night with the assignments, if this is you, it's all right. But we have drops for this section. We have 1 drop for quizzes. The homework is still open, but one of the biggest things we see with grades is it's related to doing the work. I missed the hair. I'm sorry, William. I'm sorry. It'll grow back. It'll grow back. Hair grows back. That's what I hear. That's what they told me when I cut it. So we just need to keep doing the work. I know it's a lot. It's a lot. But some people have had some really great success with coming to office hours, completing the work during office hours. So swing by office hours after class, do the work. Hopefully that gives you some motivation, some confidence right there. But who's been coming to office hours right after class and getting most of the work done? Is anyone in the chat? Like we want to give positive strategies right here, because I notice I watch when the homeworks are done, and sometimes I see people starting it at like 9, 10 p.m. at night, and then the grades are more like 40s and 50s. But I notice from what I see, people who are starting it at usually maybe 10, not 10, excuse me, like noon, 1, like right after class. I'm thinking about what time it is now. It's 9 right now. But right there, Layla says me, and I feel it takes less time. So if you are available, I know some people have work, but if you are available and you can do the work soon after we cover it, and ask the questions like, hey, Brian, I'm working on this problem. Can you show me step by step how to do it? Can you explain the process? Can we go over the results? Then we can learn right there. Office hours best. Thank you, Cad, right there. Yeah, Cad, Layla, showing up to office hours, getting the work done. And then I'm hoping the rest of your day is free. That's my goal with office hours, is you come to office hours and then you get pretty much a free rest of the day. So yeah, we can kind of get work done during the morning, and then evening is free. And I would say it's more productive too, because I'm here to answer questions. If not, watch Office Hours on the YouTube. Yeah, exactly. Watch the rewind of it. Come back and watch the videos. So I show how to do most questions. If you're stuck on one, please message me. Usually there's a similar one, or I can point you to an old video, or I can walk you through how to solve it. Just keep asking questions. Just keep asking questions. So the biggest thing we can say right here is communication. If you're stuck on something, let me know, because what we're covering right now is new material. We're covering things that a lot of people haven't done. At the start of the semester, we were covering pie charts, bar charts. This is just 2 weeks ago, right? Pie charts, bar charts, histograms, Paretos, mosaics, contingency tables, frequency tables. All these things are maybe things you had seen before. And now we're covering today hypothesis testing. And let's jump into it here in a second. We're going to try to do 2 chapters today. That's our goal. And that way we have only review on Friday. And you know how it goes. We're going to take some Kahoot questions and put them right on the test. So Friday Kahoot is basically going to be free questions. Like if you are practicing, if you are watching, taking down the questions, practicing them, you're basically getting to see a few questions on the test right then and right there. So if you're worried about the test on Friday, the Kahoot is even more important, because it's like you'll get to see test questions. That's my best sell for like, hey, the Kahoot. Also, I'll send out an update on the prizes. We do have an increase on the $20, like a $20 increase. I don't think either people have emailed me from last Kahoot either. So we might put those prizes. Please email me from the last Kahoot if you won, but I don't think I've sent either of them their Amazon gift cards. So if you won if you came in first or second, I think we did a third place, $5, I think. Please email me and say, hey, Brian, I came in this place. As long as 10 people don't email me and say they came in first, and they'll be like, wait, 10 people can't come in first. But please email me, and yep. With that, any last questions? Last questions right now. If you have it, we'll just hang here for a moment longer. But if you have any questions, let me know. We're about to hop over here and start doing lecture. But what questions are there? What questions are there? We get to hypothesis testing today. I always say these things, but this is like one of my favorite chapters, because it's a very, very important thing in statistics. Hypothesis testing, you'll have it in your project right here. So we're doing some project review. But hypothesis testing is used throughout many disciplines. It's basically one of the most classic things we've done in statistics. And what's so interesting about statistics is it's a very new discipline. Statistics has not been around for 3, 4, 500 years. Statistics and hypothesis testing, maybe 100, 150, rather new. Like the T distribution we covered yesterday with William Gossett, I think he was doing that in about 1890. So Guinness beer has been around a while too, so about 100 years. And so let's start talking about some hypothesis testing. Let's do this. So here we are with hypothesis testing. And this chapter right here is basically something I would say everyone can use. Like, it's all just about asking questions. Like, what is a hypothesis test? What are we doing when we create a hypothesis? Well, does anyone have a current belief right now? Oh my gosh, I'm afraid to ask it. I'm afraid. Like, what do you currently believe? Imagine if we had a friend, Nathan, and our friend Nathan thinks the earth is flat. So he thinks, for some reason, it's all right that your friends have different beliefs. That's totally fine. If I had a friend, Nathan, who thought the earth was flat, I'd be like, can we talk about, I don't know. If it became a point of stress, I would not talk about it with him. I'd be like, whatever. He's got an interesting belief. I mean, I have friends who think like, I have a friend who's like, so like the moon landing didn't happen. And I'm like, dude, maybe you think the moon landing didn't happen, but this guy's obviously my friend. He's another Brian. I shouldn't say who he is. But he's like, yeah, the moon landing totally didn't happen. They faked that. It was done in a studio. And I'm like, I don't see the good evidence. He's like, look at the shadow. Look at this. Look at that. We were blah, 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 blah. And I'm like, still, it doesn't convince me. It's not enough to convince me off my initial position. So when you think about this, does it make sense that we all have a what to start? Like, whenever you're talking about your beliefs, you have a what to start. It's not hypothesis. I mentioned it a second ago. What do you have to start whenever someone's like questioning something you believe? Like, maybe someone wants to tell you that cream in your coffee is the best way to go for coffee. Or someone says, the moon landing was fake. And you're like, because he hasn't moved me off that initial belief. You've got an assumption to start. You got things you believe, right? That's exactly it, Jesse. We just try to put statistics into our own mind to see how we think about these things. Like my friend who tells me all these things, I'm like, dude, you have not changed my initial belief. I can't even spell initial today. It's so much easier when the computer spells it for you. That's right? Initial belief. You have an initial, kind of like a theory. So then what someone offers to you is not a theory or game theory. I messed up that reference. But no, Jesse, you are right. Because Jesse said that. Or Tyler, great job, Tyler, right there. Let's throw out some points. We didn't throw out any points this morning. What are we doing? Let's throw out 100 points to the crowd. So we've got like a theory. We're just trying to put our own words to this. We've got our initial belief. And then someone offers to us a theory, which we'll give that name here in a second. And the theory is a what to our initial belief. I think someone says you should believe this instead of your initial belief. Like, here's what you start out believing. And someone says you should believe this instead of it. And they try to offer evidence for it. They're like, my friend is talking to me and he's like, you should believe this. You should believe this. Here's why this. And he goes through all these things. And he's trying to offer me a what to my initial belief. And this word will be key because I have this belief and he wants me to believe the other one. So he's offering me a what to my initial belief. What is he offering me? Oh, Mewbot's not awake. Let me fix that. An alternative. Great job, Zach, right there. Zach is right. Let's throw another 50 points on there. Once Mewbot wakes up right here, he'll wake up. He's offering me an alternative. I reset the computer today. It's like a challenge. That's exactly what it is, Quicksilver. The alternative is a challenge. We will call it an alternative. And this one will be called a null. We'll be looking at these words here more in a second, but does it make sense does anyone have anything to believe right now? Like, it could be that the Atlanta Braves are the best baseball team. It could be that Tom Brady's the best quarterback of all time. It could be that you're going to make an A on test 3. Do you have any sort of belief right now? And then how could I challenge that belief? How could I offer you alternatives to that belief? Like, surely someone has one belief. I believe the Nets will win the NBA Finals. Is that currently going on right now? What if I told you, this morning their 2 star players got injured. So I told you this morning, I don't know what current round in the NBA Finals. If I told you this morning, would that be good evidence for an alternative that they're not going to win? What do you think of that, Sam? I tell you, turns out in the news this morning, I'm being honest. Let's say you trust me. I tell you, there's in the news, there's a report that the two top players pulled their hamstrings and they won't be playing in the next few games. Uh, no, because they got more stars. Oh, you see, that wouldn't be enough evidence. So there you go. Sam says that's not enough evidence for me to accept your alternative, or for me to believe your alternative. Not accept. We don't use that bad A word. LeBron. If LeBron's. Oh, see, I'm so out of touch with basketball. Yeah, if LeBron's on it, game over. Game over. Turns out they did a mid-season game change or mid-season switch, and LeBron's on the other team. What other team they're playing, LeBron has actually switched over there. So would that be enough? Like, it's unprecedented in the history of NBA. It's never happened, but LeBron has switched over to the other team. So have two of the other players that he plays with, his best teammates. I don't know who they are. What would you say now? They let it go for some reason. I don't know, because he's LeBron, and they're like, "Hey, LeBron, you're the best. You can do whatever you want because he's awesome." And they switched him over, and then everyone else on the Nets got injured. Would that be enough evidence? And they're like, "This has just never happened." Oh, Tyler's saying LeBron is second best. Who's best? See, now we might say our initial belief might be, what would you say? Ooh, this is so good right here. So what if someone said Michael Jordan is the best? What if someone said Michael Jordan best of all time? That's their initial belief. That's what they hold true. And you want to give them evidence LeBron best. What would you, got a little MJ versus LeBron right here. So what would you do if what would you say to convince someone? But now you see other people have the reverse. Other people have LeBron is the best is their current belief, and you're trying to convince them, give them evidence that MJ is the best. LeBron is the best quarterback. That is no debate. Like, no one's debating Michael Jordan the best quarterback. He did go over to baseball for a little bit. He might be the best pitcher, or I don't know what he was. Outfielder? I don't know what he was in baseball. Jordan is the best. If LeBron wins this year, he is not the best. Wait, if he wins this year... Oh, MJ, you're saying would not be the best. I was so confused, AJ. I was so confused. LeBron had no first round exits. I don't even know what that is. Since I've known Julio, I've got to know more about baseball. And he'll tell me a few more things, and he'll explain to me the more importance. 6 greater than 5? Yay, that's mathematical. MJ has a defensive player. LeBron will never have that. Oh, so you're saying he's got the two components, offense and defense. He was an outfielder. MJ was an outfielder. LeBron won the home run derby. Oh my gosh. Okay. So I think we understand. We're all putting evidence in the chat right here. We're all trying to convince someone off an initial belief. So someone has an initial belief, MJ is the best, and we're trying to offer evidence to them that LeBron is the best. Jordan, Kobe, LeBron, that's the facts. Can't argue with that, Anthony. Let's draw some 50 more points. That's what we try to do right here. Try to have a little bit of fun and try to see how we offer evidence. That's all you're doing right now is you're just offering evidence. I mean, AD can potentially be a defensive player of the year. Okay, who's AD again? Is that... I don't know which one. Is that a position? People are saying LeBron is greater than Kobe. Oh man, this is all the viewpoints. Anthony Davis. Okay, I think I know that name. It's really, I don't know. It's making jokes. A hypothesis test. Here we go. So we've seen this before. Anthony Davis is AD. Oh, see, I'm so bad with basketball. I'm just growing up. Here, we'll go back to the slide here in one moment. Who did we? I liked. It was so funny. We would get a lot of sports cards. I should wear my sports shirt today, and we got one for the. Can't remember what team it was. The Spurs. We got one for the Spurs. But you know who I really liked? We got one for the Spurs, and it was like if they won, we won something. It was like from a Topps pack, and so I would root for the Spurs. And then my friend was a big fan of the Celtics, so I'd root for the Celtics. That's back when what was his name? Oh, Nate Robinson was on the Celtics. Can't remember who else. They called him Big Baby or something. Nate Robinson like hopped on his back during one of the playoffs. It was really cool. And but Nate Robinson I always thought was awesome. Just like dude could like dribble and just like some dude's like a foot taller than Nate Robinson's just like choo 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 and just like jukes around him and then just like dunks and you're like, what the heck just happened? I mean, you talk about skills. I'm gonna put Nate Robinson up there with some top like ball handling skills and some top just like Nate Robinson. Like when you talk about like the fundamentals, that dude right there can just like run circles around everyone, literally. But yeah, no. So I'm you know what I'm doing? Initial hypothesis. Nate Robinson best. We're putting Nate right here. Nate is the best. That's Brian's initial hypothesis. You're gonna have to convince me off of that. So your theory is LeBron's the best. My theory is that Nate's the best. I'm going with that right there. So what are we doing right here? We are doing null hypotheses and alternative hypotheses. And we see this all the time, especially in like criminal trials. There's an initial hypothesis in a criminal trial. And in the United States, people, oh no, why did Nate let us all down? Oh, is it the, oh yeah, I forgot that recent news. Oh my God. Yeah, forget. I'm not up to date on news. So there was the initial hypothesis, what we currently believe, and this is going to be called the null hypothesis. So in a criminal trial, people are presumed what until there's evidence of what? What are people assumed to start out with until there's evidence of what? And this is how we do it. And be careful here because we're not going to say they are this. We're just going to say we have good evidence to believe this. They are assumed innocent until we have evidence. Now, we do say proven guilty in a court of law. We do say those words. We say like proven guilty. But, and this is what really sucks about just, I can't imagine a perfect system. Our system is far from perfect. But are there innocent people who go to jail? You can look at the settlements that happen. There are innocent people who go to jail, or people who we later find out we have good reason to believe they're innocent. And there's things like the Innocence Project, major things like that. And, you know, it's just a really not good. And especially when you look at older cases, like cases from the 70s and stuff, where they're like, this person was walking in the area a day before the crime happened, and they usually aren't in this area. They're guilty. And everyone's like, yep, they're guilty. And you're like, what are you doing? What would you say to me? Would you say that's enough evidence? Like, here, let's put Brian on trial right here. We need like that. Let's go grab a courtroom right here. Let's go grab a courtroom from Google Images and put Brian Stevens on trial right here. So let's go to copy image and let's go grab this courtroom. Let's go put Brian on trial right here. There we go. There's the courtroom. Let's head over here and go on trial. Watch. Oh no, Sarah, that's so sad. Hopefully, oh, I'm sorry to hear that. I'll bet you. Watch this. Wait, you ready for this? Oh my gosh. Here we go. You know what? I tell you who's gonna come here and be the. We're gonna have a guest of honor, and the guest of honor. We're gonna do a few people here. We're about to put Brian on trial right here. Brian Stevens on trial. I'm too afraid to ask what Brian's on trial. Oh, there we go. Got to shrink down right here. Oh no, now I'm on trial. Okay, let's bring in our guest of honor. Our guest of honor to be the courtroom judge is going to be Mubot. Mubot's right there. Judge Mubot.
Brian is on trial. Let's do this. My voice is too. There we go. Now it sounds better. Judge Judy. We don't got Judge Judy. I gotta work on my voice.
Okay, Mubot is here. You know who is saying they got attacked? Everyone knows who's saying they got attacked. Oh no. Oh no.
Tiny Brian's green screen's not working. What'd you do, Brian? Tiny Brian over here. Why is my green screen not working? I should have never changed anything. What is going on?
I have no idea what is going on, everybody. I don't know why the green screen changed. I didn't try to change anything too much. Fail on this right here. Where's negative Mubot? Oh, we could bring him over here to this world. Let's bring him over here to this world real quick, and then we'll get serious here. You ready? Let's go grab other Mubot. Here we go. We got to go grab him and bring him over here. We got everyone here. Everyone is all here right now. And let's go grab other Mubot. So other Mubot, where you at? Evil Mubot. Here, let's go over here to the main world. Bring Evil Mubot over. He doesn't get, we don't see him that much. So let's bring Evil Mubot over here. He can be brought over here. There we go. Look at that. He needs to shrink down a little bit. Oh my gosh. Brian, we never get to see Evil Mubot. We never get to see Evil Mubot. We got everyone here right here. So let's see. With everyone here on this screen, let's find out. Brian is on trial right now for trying to kill off Evil Mubot. So Evil Mubot is saying Brian tried to kill him off. Hey, Brian, you stop talking right here. Let Evil Mubot talk. You guys. No.
There we go. I'm Evil Mubot. Brian tried to kill me.
Okay. We know what happened right here. That voice is impossible to understand. But what is the null hypothesis right now for Brian's guilt? Who can tell us the null hypothesis right now in the court of law? Who can tell us the null hypothesis in the court of law? What is the null hypothesis in the court of law right now for Brian and all the Mubots? Did I order the code red? Wait, what? Like the Mountain Dew? What is the null hypothesis in the court of law right now? The null hypothesis is that I'm innocent. So starting out here with Brian on trial, the null hypothesis is that I'm innocent. Let's see what they have to say.
Brian was found outside Evil Mubot's house walking around at 2 p.m.
Okay, I was walking around Evil Mubot's house at 2 p.m. Who is rejecting their null hypothesis right now? William says I'm guilty to start. But the only evidence they have right now is I was walking around Evil Mubot's house at 2 p.m. Who thinks I'm guilty right now? Who's like, Brian is totally guilty. I reject my null. Brian goes straight to jail. Do not pass go. Do not collect $50. Who thinks? When did the cry occur?
Mubot screamed out, Evil Mubot, I'm good Mubot. Evil Mubot screamed out at 2 a.m. and Brian was walking around at 1:45 a.m. on the camera.
So what happened right? What do you think now? The crime occurred at 2 a.m. and Brian was out there at 1:45 a.m. I was outside Evil Mubot's house at 1:45 a.m. What do you think now? That Brian is guilty now, or what do you think? So all they have is I was walking outside the house. I mean, you might say that's a lot. You're walking outside, still innocent, Zach says. So what are you doing right now? Are you accepting your null hypothesis, or are you just staying with it? What do you think? How would you phrase this to someone? Would you say, I know Brian is innocent, or I don't have good reason to think he's guilty? What sounds better? I know Brian is innocent, or I do not have good reason to believe he's guilty. How would you phrase this? Just talking about someone who, I'm on trial right now. Just talk about, like, you're watching Brian's trial and you'll say, would you say, I know he's innocent? Or would you say, I have good reason to believe he's not guilty? Like, I do not accept that alternative. I do not accept the prosecution's claims of Brian's guilt. Why are you walking around someone's house at 1:45? Well, Evil Mubot had been saying mean things about me, so I was going to talk to him about that. I don't know. I was just going to be like, hey, what's up, Evil Mubot? And I don't know. I don't know. And I'd brought some stuff to, delete computer programs, but just, I don't know. Haley's with the prosecution here. Haley's on the prosecution team right here. Haley, keep up the prosecution. Like, what were you doing? I'm on the fence. I don't have good reason to believe he's guilty, but who's lurking around someone's house at 1 a.m? Jesse, Evil Mubot's been mean to me in the past, and Evil Mubot really shouldn't treat people that way. That's really bad of Evil Mubot. He gives students bad advice. He really needs to go away. Students who listen to Evil Mubot are doing bad in the class. So frankly, I just want Evil Mubot to be gone. And I'm just saying, if something had happened to Evil Mubot, I wouldn't be too worried about Evil Mubot. I'm just saying that if, Evil Mubot disappeared, went away, gone, Not that big of a deal in my book.
What are you saying, Brian? You don't like Evil Mubot? We also have on camera that you were wiring into the internet on Hit House trying to delete him.
Oh God. Oh no. I do not know. Who's starting to reject their null hypothesis now? You're starting to maybe go over. I think Haley's with the prosecution team right here. But who's starting to should have gotten rid of the evidence? So we it could be a motive, but he went with the intent to destroy his property. So all of a sudden now, and you could be wrong. That's the thing about, especially with the court of law right here. And we try not to do this. This is once again a major problem in America, or in any country that has to do trials, which is any country. But we are starting to maybe at this point starting to bridge over into rejecting our null hypothesis. And it could be that Brian's still innocent. You could make an error. We'll cover that later today. But let's head back here to the main screen. Here, I'm going to have to... Evil Mubot. Oh, we're all getting deleted. Bye-bye. 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 Go away. Let me move myself back down here because I'll need to be down here when we come back. Oh, I got to look what happened to Tiny Brian's screen. What did I do? I was trying to... When I was filming the stuff this weekend, I made some changes. And I must have somehow changed a filter on a camera and taken it off. I'll fix that later today. Where's Puppet Shark? Puppet Shark, is Brian guilty? This is not going to be good for me. Oh, we didn't even hear him. He didn't. Oh, no. Puppet Shark with the verdict in. Deacon, they got me in 4K, man. Puppet Shark knows what's up. Tiny Puppet Shark knows what's up. Their verdict's in. Brian's guilty. So what you just saw in that court of law example is what we go through. We're not saying case closed. I should put the hammer on, like the gavel on there. So what we have right there is a court of law example where someone is on trial and we start out believing they're innocent. And as evidence comes in, we are either going to stay with our belief that they're innocent. And we don't call that accepting innocent, at least in statistics. We don't say, I accept that they're innocent or I know that they're innocent. We would say, I continue to believe that they're innocent. Or we reject that belief that they're innocent and we go over to an alternative that they are guilty. So how does this look in statistics? This looks super complicated, but all this is saying is the null hypothesis states. That's the null. HO is the null hypothesis. What is the null hypothesis? The null hypothesis is just our initial belief. This is what we start out believing. And then we're going to state that some parameter. Can anyone tell me a parameter? Remember, here, I'll draw something down here on the bottom. Here's a hint for what are parameters. I'll put SS. Those are not parameters. Those are sample statistics. PP. Can anyone tell me the associated parameters right here? And these are the two we're really going to care about. So I'm putting here sample statistics. That last one is a sample difference. Can anyone tell me the associated parameters on the other side, which is what we're going to test? Remember, SSPP. Sample statistics give us estimates of population parameters. So what are some of the population parameters? I'll mark them in red right here that we're going to test. And these are the things that will go right here. So I've got the sample statistics. We're not going to test sample statistics, so those won't go there. I'm going to put the population parameters we're actually going to test. You have chapter 15, has both of those, and then chapter 17 is the y bar minus, we'll put it here in notation. What are some of the population parameters we will test? 20 points each. Let's get them all right here. What are some of the population parameters? Let's throw out some points here. You know what? Just for that example, everyone was so interactive. 50 points right there for the example. What are some of the population parameters we'll be testing? Close. Actually, Zach, everything but, because rho is technically correlation. Oh my gosh. Zach, I made an error. This should be p hat, because that's the sample proportion. And Jesse, we could do sigma. We could test the true standard deviation, but we'll do mu. We'll do p, which that's the only one that's not Greek letters. And then we will do mu1, and that is a delta. Some people use a delta to do this because that's a change in or a difference. So you could, no, Jesse, that was a great answer right there. Sigma can be tested. We just don't do it in this class. So we could test sigma, but we don't do it. It's just one thing we don't do. Oh, no worries. Because S is sample standard deviation, and we could do sigma. That's just not, It's just not covered in this class. But there are tons of tests where people test the sample or the true standard deviation. I'm losing my words today. So we're going to put into this bracket right here. I'm going to highlight the ones we cover. We just don't do sigmas. There's just tons of things we could cover in this class, but we don't. And they're going to go right here individually. So what Brian's going to write right here is he's going to write a test. And I need you to tell me, Brian is testing the what now? What is Brian testing about a population? He's testing a what? Brian is testing a what? You remember your notation. This is the sample proportion. Brian is making a statement that he currently believes the null hypothesis is that the what is equal to some hypothesized value. Just read it as is. The null hypothesis states that the two words right here, the something, something, and this was sample proportion. Don't say sample. Brian is starting out by saying, my null hypothesis is that the true something is equal to some value. And I'll even put what this value is in general notation. Well, we'll see it here on the 2 slides in a moment. The population proportion. This is population proportion. I'm saying that I currently believe that the true proportion of students who eat at Taco Bell once a week is 70%. I currently believe that. I currently believe, great job, Jesse and Zach, right there. I currently believe that the true proportion of students who eat at Taco Bell once a week is 70%. I currently believe that the true proportion of students who own a dog is 30%. I currently believe that the true proportion of students who take summer classes is 20%. I currently believe that the true proportion of students who have had Stats 201 at the University of Tennessee is 72%. What can the hypothesized value be? Now, there are some limitations to it, but do you notice how I'm just coming up with different proportions? The hypothesized value, which in this instance is P sub 0. Sub 0. New Mortal Kombat movie, pretty good. What can the hypothesized value be? What can the hypothesized value be? What can it be? What kind of values can a proportion be? The hypothesized value can be anything. It's just something you're hypothesizing is true. Does that make sense? Like I'm just saying the true proportion of students who like Taco Bell is equal to, and then you just hypothesize a value. And does everyone see it's got the O, like the null has the O? I guess I could do, I think they did sub 0 right there. There's a sub 0. So what we have right here is that the true proportion is equal to some hypothesized value. But let's switch this up. And I want you to read this as a sentence now. I'm going to read this as a sentence, right? I'm going to put in the chat. The true proportion is equal to some hypothesized proportion. Okay, that's how that reads. Now, I'd like for you to read. Where's insert symbol? Oh my gosh. Oh, good. Where's Mew? Really? I might just go grab a Mew online. Insert equations, much easier. Here we go. There we go. Read this right here. This is key. If you can read this, who can read this right here? Look at what I just put in the chat and see if you can read this now, because this is another null hypothesis. So how does this read? So look at what I just wrote a moment ago. And I had a moment ago, the true proportion is equal to some hypothesized proportion. So how does this read? This is a different null initial hypothesis in statistics. We're using all of these population parameters. How does this read as a sentence? Like if you just look at this right here, and you would say the null hypothesis states, that's what that reads, the null hypothesis. So how does that read? The true mean is equal to some hypothesized mean. Yep. So you might just say like the true average height of UT students is equal to 68 inches. You just hypothesize a value. That's what you're just hypothesizing is true. That's what you're going to test. And then the last one right here, if you look at this, what does this mean right here? And I think we actually have to highlight. What is this going to mean right here? Try reading this one as a sentence right here in 2 seconds. Oh my gosh. There we go. How does this one read? And this is the last one we'll do. What does this mean right here when we have two means and we're looking at their what between them? This is what Zach was alluding to a moment ago. We have two means and we're just looking at the what between the two means and we're stating that it is equal to what. This is the last one we'll cover. So this is our null hypothesis right here, and we've covered all the different null hypotheses. I want to show you something about them in a moment. So what do you notice about this one? We're just saying the null states that the what between the two whats is equal to what. The null states that the what between the two whats is equal to what. The difference between the two means is equal to 0. Exactly, Zach. The null states that the difference between the two means is equal to 0, or the true difference. Yeah, Zach put the true means, the difference between the two true means is equal to 0. Yep. The true difference between two means, or the difference between the two true means. Exactly. Either which way, we're just talking about like for the population. So how are we doing this? Let's look at how to write the null. The null has to it three parts. The three parts to the null hypothesis are, wrong color right there. The three parts to the null hypothesis are 1, a population parameter, 2, an equal sign, 3, a null value. Now you might say, okay, that's a lot to get down, a lot to practice knowing how to write the null. But here's where things get really easy when we write the alternative. What do you notice is the only difference between the null and the alternative? Oh, we call it hypothesized value. What do you notice is the only difference the sign? Exactly. The null has the equal sign. The null has the equal sign. Great job, Layla, right there, 20 points. We were saying that during office hours yesterday. The null has the equal sign. Great job. The null has the equal sign. Exactly. And we're going to pick one of those. Great job also right there, Sam and Zach and everybody. Let's highlight this. And we'll put right here, pick one. Okay. So what would you focus on practicing writing right here? If you can write the null hypothesis, you can then write the alternative. So the reason I show this right here is once you know how to write the null, you can write your alternative. You just change the sign. And I see so many people, oh no, I see this all the time because we put trick questions on the test. Like, not trying to trick people, but the null and the alternative have all the same values. You just change the sign. Like, I'll show you an example right here. Let me go to one of the slides that has it. But when you look at a null and an alternative, they just change signs. We surely have one on here. We're just showing the null hypothesis? No, come on. Oh, here we go. What do you notice? Repeat what Layla said earlier. What do you see about the null hypothesis? The null has the what? And what are we testing right here? The null has the equal sign. The null has the equal sign. Exactly, Leanne. Great job, Leanne, right there. The null has the equal sign. And then when you get to here, all you're changing is the sign of it. All you're changing. Same values. We got P, 0.07, 0.07. And then all you do is change the sign. That's all we change when we write the alternative hypothesis. We just change the sign. So you have to just pick according to the researcher's question. So once again, we are testing population parameters, and then we'll use the sample statistic to get insight into this. That's why it's called inferential statistics. Here's the three different alternatives. Once again, we're showing this here, though, to show that all you're doing is picking one of these. You don't use all of them. I've had people get to this and be like, I have to write all of these. And I'm like, no, 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 no. You will pick one of these three right here based on the question. Great job, AJ and Zach and Sam. So right here, how do we pick the alternative? This appears on the test. We don't pick based on the data. We don't let the data tell us the answer to the question, at least what way we're deciding. If someone wanted to show that COVID numbers, is true. COVID numbers this month have had a significant decrease. What alternative do you think they would pick? Alternative 1, 2, or 3. If someone wanted to show COVID numbers this month had like the proportion of people who get COVID, and this would be P, and it would be equal to whatever last month's numbers were, and the alternative would be the proportion of people who got COVID is what to the hypothesized value, which is last month's. So we would be trying to say that it is what? We're trying to show it's gone down. So the researcher is saying, have COVID numbers gone down? Do we have good evidence of this? And they would use the first one right there. So they're trying to show evidence that the true proportion of people who have gotten COVID has gone down. Does that make sense? And this would say the alternative states that the true proportion of people who have COVID is less than the hypothesized value. So that is where we use the researcher's question. We don't look at the data for the question we're asking. Now you might say, well, what if the data shows otherwise? Well, then we can't reject the null hypothesis. The data is going to let us know whether we have evidence for the alternative or we don't have evidence for the alternative. So how does this look in practice? Well, right here you'll see we have our null value. Our null value is the most likely value to occur. It's at the center of the curve. Now we take our observed result. So here's the observed result. And then we plot it on the curve. Now there's something really interesting going on right here. We're going to talk a lot about this here, because you'll notice we also plot this right here. And let's talk about how to plot p-values. So this is how to plot p-values. And we're going to go over here to the Word document and show how to write p-values. Let's leave the courtroom for now. Okay. So we have 3 different alternative hypotheses. With our 3 different alternative hypotheses, we have a greater than, less than, or a what alternative. What was the last alternative we had? Greater than, less than, or what? So we have greater than, less than, and what's the last alternative? Greater than, less than, or what? Does not equal to. Great job, Leanne, right there. Let's throw some 20 points. Excellent work. Greater than, less than, or not. Great job, AJ, too. Greater than, less than, or not equal to. So how does this look in practice when we draw them out? Well, when we do the less than, we want to go to wherever our result was, and we are going to shade below it. Whenever we do the greater than, we'll go to our result and shade above it. Does anyone notice what percent of the curve, the greater than and the less than, if you were to add them up together, what percent of the curve they shade? This definitely appears on the test. The greater than and the less than, when you look at the 2 results, shade what percent of the curve? If you look at the greater than and the less than result together, they shade what percent of the curve? Now, you wouldn't put them together like that. I'm just taking them and showing them together like that so you can see that the greater than and the less than shade what percent of the curve. We think about a greater than test and a less than test. What percent of the curve? They add up to 1. Exactly. They're complements of each other. So you can, if you know what the greater than test was or the less than test, you can know either one. So you might say, well, what about that does not equals test, Brian? Well, the does not equals test, we need to take, and this is going to be the easiest way for me to do it. And here we go. Let me reverse it. There we go. Perfect. So it's right there. And actually, let's take this. And you can see what I'm doing mathematically because I'm making sure I'm doing this accurately. And then let's go here and do the following. If I told you that, blue. If I told you that this was 2% of the curve, how much would the greater than test be? If that right there is 2% of the curve, how much is the greater than test? Might not look like 2%, but it is. How much is the greater than test? Like, how much is to the right of it? 0.98, exactly, 98%. So this one here is 98%. We'll just put 98% right here. then how much is the does not equals test? And if you watched carefully, when I did the does not equals test, I made sure I did it a certain way. How much would the does not equals test equal? So we're taking 0.04 exactly. The does not equals test is double the smallest. The does not equals test is double the smallest. Because if you notice, this was the same thing. I just reflected it on the other side. So this is a result just as extreme on the other side. So once you know one p-value, you know them all. And I mean this. On the test, here's what we do. I'm going to try to like block it out so you can't see it. But on the test, we have questions. So you're hearing test questions right now. We go here and we do a statistical test. And we go and we test the heights of students. And I'll give you a test question right here. Let's go here and do a test. I need to look at the standard error. Okay, so 67.5. I'm coming up with a value that won't make a ridiculous p-value. This is how you do the test of a mean. Once you go to analyze distribution, you're going to go here and type in the tested value. I'm going to test to see if students are actually 67.5 inches tall on average. And there's the test results. And we did get, there's decimals we can't see in the background. So here's what we do. I see you can see the answers. That's so not fair, though. So we go here, and we blank out the numbers. Ooh, that's a hard way of doing it. You could definitely do it. Okay, so we've seen the answers. Good question right there, Leanne. Here, I'll explain that in a moment. Like, why did I choose a certain value? Great question. Here, we'll do this, and I'll explain that next. Great question. So you've probably seen the answers to this, but I want you to tell me mathematically, how are you going to get? So this number right here is the less than test, which is actually this amount of area over here, which it's hard to see that I'm shading that. But how are you going to get the greater than test? Show me mathematically how to get the greater than test. You might have seen the answer, but show me mathematically how to get that yellow shaded area right there, which is the greater than test. Show me mathematically how to get that. Zach is correct. We're just going to subtract from 1. So you can see here the less than is less than that red line right there. And then the greater than is above it. So that is just going to be that number right there. Now, how are you going to get the does not equals test? How are you going to get the p-value for the does not equals test? And this one will be a little bit different. The does not equals test is the shading on both sides. So now we're interested in this right here, the shading on both sides. And if you ever wonder which one to double, p-values have to be between 0 and 1. So if your p-value is over 1, then yep. And Zach is correct. We're just going to double it. There's some decimals we can't see in the background, so that's why it doesn't, you'd be like, wasn't 2 times 6, 2 times 3, 6. There's decimals we can't see. So great job right there, Leanne, Zach, Chase, everybody. Yep. So is it making sense how these p-values are found? That the less than and the greater than, and you can see the signs right here, less than and greater than, and then this one says greater than absolute value of t. This one says greater than absolute value. So this is your does not equals because of the absolute value. It's like one just as extreme on either side. So this is the does not equals. This is the greater than. This is the less than. And what do you notice about the less than? What way does the less than shade? And look at the less than and look at the way it shades. The less than always shades to the what? Just notice how the less than works. The less than shades to the which side? So whenever you do a less than test, you go to your result and you shade to the left. Exactly, Leanne. Yep. And so Leanne asked such a good question right there. They asked, well, wait a minute, why did you use 67.5 and not 67.7? So if I use 67.7, what do you think? And we'll talk more about this, but what do you think would happen to my p-value if I use 67.7? Do you think that would be more or less likely? If I use 67.7 as a hypothesized value, do you think that'd be more or less likely? And then I'll show you how we'd actually do a test before Like here, we'll just see if this is more or less likely given our sample results. Do you think 67.7 is more or less likely? Given our sample results, what we see in our sample right here, I tested 60, it'd be more likely because it's closer to the sample results. So what we saw is more likely true if we test 67.7. You'll see bigger p-values right here. There'll be more shaded area under the curve. And then I'll talk about how we would actually do this in practice, because I didn't do it like the actual in practice way. And you see the p-values are much bigger here. They're even like way closer to 1. How could I make this p-value exactly 1? Well, if I want to make that p-value exactly 1, well, then I could test literally this value right here. If I put in that value to all the decimals, which is not something we would do. This is not how we do statistics. We should get basically a p-value of 1 right there, because we saw exactly what we expected to see in our sample. We hypothesized that this is true, and then we saw this. So this is telling us right here that this is the most likely thing to occur. What if I hypothesize, what if your friend told you, I think UT students are all like NBA players? If your friend told you, I think UT students are all NBA players, I think they're all 6'6", your friend thinks that is true. And you say, I don't think that is true. I think they're much shorter than that. So you'd say, I think UT students are much shorter than that. They say, okay, well, let's go out and collect data on 628 UT students. You say, okay, let's go do that. Let's go talk to 628 random UT students, which is less than 10% of the total population. Make sure the distribution is nearly normal. And let's go test your theory that UT students are 6'6". Does that make sense? Your friend has an initial hypothesis that UT students, so the whole point of this is to test a value which is different. Exactly, it might be different or it might not be different. Your friend believes right now that UT students are all like basketball players and like they're all 6'6". Does that make sense? That your friend has this initial belief and you're saying, I don't think that is true. Ooh, let's do this. Before we run this test, let's go here and write the null hypothesis. I'd like for you, as we write this null, to tell me what goes here in blank 1, blank 2, and blank 3. So let's write the null hypothesis. Your friend currently believes that UT students are all 6'6". 6'6" is 78 inches. Put like 1 equals this, like this is a wrong answer. 1 equals P. No. The first thing, P equals, oh wait, you're so close, Layla. You're so close, Layla. That would say the true proportion of students is equal to 78 inches. So you're so close right there. That is so close. For this part in the project, do we choose a random mean? Yeah, you can choose a random one. Yeah, it makes something that hopefully makes sense. You could ask me if you want. Zach, you got it correct, because we're analyzing quantitative data, so it'd be the true mean. So the way to know if it's mu or p, if it's means, like this one where it's height, it'll be quantitative. And just say to yourself, the true proportion height of students is equal to 78 inches, or the true mean height of students equals 78 inches. Layla first right there, getting everyone 50 points. Always those first answers, because when you go first, you don't get to see their answers. So we have here that the true mean height of UT students is equal to 78 inches. What do you think your alternative is when you say to your friend, that's crazy, they're much shorter than that? You say to your friend, that's crazy. Oh, I got to write alternative here. That's crazy, friend. You think the moon landing's fake and the earth is flat, and you think UT students are 6'6". I think there's good evidence they're much shorter than that. I think there's good reason to believe that UT students are much shorter than that on average. What would be the alternative here? The alternative would be exactly mu less than, exactly. Good evidence that the true mean is less than this. So we're saying that there's good evidence, or we're going to see if there's evidence. We're going to examine this to see if the true height of students is less than 78 inches. So let's go ahead and run this test right here. And what do we see in the test? Go away. What do you notice about our observed result? What do you notice? Our observed result is down here. Our p-value for the less than is tiny. Did we land far away from our friend's hypothesized value? Like, you can't even really see it. Did we land really far away from what our friend hypothesized is true? Trying to get so we can just like see this. Here's what our friend hypothesized as true. Here's where we landed. So does this look really possible given this is true? Here's what they say is true. 78 inches is the truth they believe currently. And here's what we observe in our sample. This is our sample result right here. There's the sample result. So it does look possible or it does not look possible. Not saying it's impossible, does it look probable, I should say. And that's what the p-value is showing right here. This p-value right here, don't worry about reading that, but it's so tiny that we're saying that this is basically impossible by random chance, given 78 inches is true. Does not look possible. Exactly, Zach. So what would you do to the null of 78 inches? What would you do to your friend's initial belief of 78 inches? You would go to that initial belief and you would reject that initial belief. And you would have good reason to believe this right here. You're going to reject the initial belief and have good reason to believe the alternative, that they are less than 78 inches tall. And that's what we're talking about when we do p-values. So p-values are letting us know if we reject the null or we do not reject the null. Because all a p-value is just a probability. P-values are just probabilities of getting our sample result or something more unusual than that given the null is true. So if you think about it, if Brian were to tell you the null hypothesis is Brian can run a mile in 6 minutes. Oh, God. The null hypothesis is Brian can run a mile in 6 minutes. You observe Brian running a mile in 12 minutes. He is out of breath. What would you do to that initial hypothesis? Just use statistical wording once again. The null hypothesis is you observe Brian running a mile, or the null hypothesis is Brian can run a mile in 6 minutes, and you then observe in a sample, there's Brian. You then observe Brian running a mile, and oh gosh, it's supposed to not do that. You would reject it, exactly. You'd say, Brian, there's no way you can run a mile in 6 minutes if I observe you running it in 12 minutes. But let's say a different day you went out there, because maybe I was doing like a long, slow distance or something like that. You observe Brian running a mile in 6 minutes, 1 second. Now, did I run the mile in 6 minutes? Did I run the mile in 6 minutes? The answer is no. I didn't run the mile in 6 minutes. But what would you believe given this sample result? That me running a mile in 6 minutes is what? You try to use statistical wording right here. So you observe me running the mile in 6 minutes, 1 second, but I didn't run it in 6 minutes. I didn't do exactly what you believe currently. But you would tell me this result right here that you saw was what given 6 minutes is true. You would say to me that this result right here is very what given 6 minutes is true. And that's what we're talking about with a p-value here. The result of 6 minutes, 1 second seems very what given 6 minutes is true. If 6 minutes is my true mile time, it seems very likely. Does that make sense? Like a high p-value. That's what a high p-value means, is like what we saw was likely given the null is true, or a low p-value is this right here because this seems unlikely given the null is true. Does that make sense right here? While this one would have a low p-value and the other one right here with 6 minutes, 1 second, I can still be out of breath. This one would have a high p-value indicating to us, I'm still out of breath. So this one right here would have a high p-value because it's likely that the null is true. So likely null is true. Given our sample result, it's likely the null is true. Brian didn't do exactly what we thought, but he did something that is probable given the null is true. When we change it to 12 minutes, 1 second, now the p-value is low, and we would say that this sample result is not likely given the null is true. So it's not likely that we would observe Brian running his mile in 12 minutes, 1 second. Given the null is true, we reject the null. So let's put that last bit of wording right here. Reject the null. That trap keeps getting more oblong every second. There we go. An oblate spheroid, just like the Earth. So we now, I shouldn't change this up. Does this make sense right here? How we do things? I think we don't realize this, but we do statistics all the time in our mind. Like we reject alternatives, or we reject nulls, we accept alternatives. I shouldn't say accept, we take in alternatives as new beliefs. So with this right here, we have beliefs and we change them when there's what? What is this right here? With our current belief, this would be new what to challenge our current belief. What would this observation be? And this is how science works, which is so awesome. This 12 minutes, 1 second would be new what to challenge our current belief. Think of an E word, which is what statistics looks for. It looks for this. What is statistics looking for? It's looking for this sort of thing. Evidence right there, Zach and Layla. Great job. We're looking for evidence. So let's take a look at this p-value. When we have a p-value is the probability of seeing our data results or results more extreme. Great job, Chase and Deacon. More extreme given the null is true. And the p-value is always a conditional statement on the null being true because we believe in this current moment the null is true. Brian told you he's a 6-minute mile runner. So you're like, yeah, Brian's my friend. He's a 6-minute mile runner. I totally believe this. And then someone says, you need to go out to the track and watch him run a mile. And you go out to the track and watch him run a mile. And you're like, oh no, Brian, no, you said you ran the mile in 6 minutes. No, you run it in 12:01. You were supposed to save us all. No. He's slow. 12-minute mile is not horrible. I used to be fast. So we only have 2 phrases right here. And I want to point something out. This is the very classical statistical way of saying it. If I could change the world right now, if I could just like Thanos snap and remove this phrase from all of history, I would, because all this phrase right here means is either you reject or you do not reject. Have to be very careful. I said the bad A word today in class. I said the accept word. We don't say that word because we either reject or we do not reject. I want you to think of the following phrase. I either go to the mall or I what? So just look at these words right here, and I want you to use the way Brian wishes the way the world was. So I either go to the mall or I do what? Brian either will go to the mall or he will what? Brian will either go to the mall today, which I probably won't. So, or Brian will what? Think of complements. Think of law of non-contradiction. Well, Brian either goes to the mall or does not go to the mall. So Brian either goes to the mall or I do not go to the mall. Like, what are we talking about here, Brian? I don't get it. Why are we talking about you going to the mall? Because Brian either goes to the mall or Brian either go to the mall or does not go to the mall, or Brian fails to go to the mall. Does this make more sense right here if you hear this? I failed to go to the mall today. Let's put it that way. I failed to go to the mall today. If I said this, what would you believe about me going to the mall today? If I said I failed to go to the mall today. You say, how'd your day go? You say, I failed to go to the mall today. It's such a weird way of saying it. Thank you, old-timey English, for making statistics harder to understand. But if I say I failed to go to the mall today, I'm just simply telling you I did what? Because I either go to the mall or I what? And this is all this phrase means right here. If I say I failed to go to the mall today, you'd be like, you failed to go to the mall? I say, yeah, I failed to go to the mall. I didn't go. I failed to go to the mall today. I did not do that. So you either reject the null or you do not reject the null. I'm totally fine in this class. You have to know fail to reject the null because it's so common. Hopefully, I know I ask things like this a lot, but has anyone ever heard someone say, I fail to reject the null? Like all they're saying is, I do not reject it. That's all they're saying. I might write a paper about this. Maybe it would get published, but I would say it's time to change the words here. It's time to stop with tradition. I fail to reject the null. No, I just do not reject the null. I do not reject the null. That's all that means, because it's just you either reject or you do not reject. Maybe Brian can change the world. If I can make one change in statistics, this would be it right here. Just make it easier to understand. I do not reject the null. That's how we do it in genetics. Yeah. And that's why I have to teach it this way. Like, even if I were to write this paper and people were to be like, yeah, Brian makes a good point, it would take years to change the paradigm of the way people speak. You have to know the phrase fail to reject the null because it's what people do. And we don't just teach you how to understand statistics. We also teach you how statistics are used. So you will hear the phrase fail to reject the null. And it just means I don't reject. It just means I'm staying with the null. I don't have reason to go against it. So we only have two choices right here. We either reject the null or fail to reject the null. And here's one of our favorite phrases in the class. Our phrase is, I'm trying to find a space to type right here. When the p-value is low, reject the null. Let me go right here. When the p-value is low, reject the null. When the p-value is high, just let it fly. So what do we mean by just let it fly? So when the p-value is low, reject the null. When the p-value is high, just let it fly. What do we mean by this? What do you think just let the null fly means? When the p-value is low, reject the null. That's pretty obvious. If the p-value is lower than some threshold, reject the null. If the p-value is high, and I might be able to do something really nice right here. Watch this. What do we mean by just let the null fly? Sure. What do we mean by just let the null fly? So when the p-value is high, just let the null fly. Do not reject. Exactly, Zach. So when the p-value is high, just let it fly. Fail to reject. Just don't reject the null. When the p-value is low, reject the null. When the p-value is high, just let it fly. Just rhyme those words together. When the p-value is low, reject the null. When the p-value is high, just let it fly. Now, this will come in a lot of use, but what do we mean by low? When the p-value is lower than alpha. We'll have a lot of talk about alpha here in a second, but alpha is going to be this symbol right. I'm going to draw in red. Alpha equals 0.05. Alpha is the threshold. So this is going to be our alpha threshold, and whatever we see for our p-value, if the p-value is lower than that, we reject the null. So all you have to say is, what's my p-value? And we can see this in our statistical test. Let's go bring a statistical test up right here. So you can see it on the screen. For this statistical test right here, do we reject the null? Let's go full screen on. Do we reject the null for this statistical test I'm pointing at right here? And look at, you can see what it says. It's telling you this p-value of 1.7 e to the negative 255 is small enough to indicate very convincing significance. P-values are the probability of getting an even more extreme statistic, given the true value being tested is the hypothesis value, usually at 0. Ooh, not usually at 0. I need to talk to Jump about that. For the two-sample t-test, it's usually 0. But yes, we should definitely reject it. This p-value is crazy low. We should reject. Now, we don't reject for this alternative right here. That's a very high, so is not significant as it's saying to you. And this one right here, we would reject also. So it depends on which test we're doing on if we reject or do not reject the null hypothesis. So remember, when the p-value is low, reject the null. When the p-value is high, just let it fly. All those alternatives. So the way we shade, and we've seen this earlier, is dependent on the alternative we pick. If we pick the does not equals alternative, this is called the what-tailed test. I want you to put a number in the chat. What do you think we call this? It's called the sided or tailed test. A lot of times I'll say it's a two-something, or there's the answer. It's a two-tailed test. This is the two-tailed or two-sided test, the two-sided alternative. Exactly right there, William. Great job. It's a two-tailed test. And then you can also see the one-sided tests, and we have two of those. We have a less than, and we also have a greater than. It's kind of weird to do the greater than test right here. Who can find the p-value for the greater than test? Pretty easy test question right now. What is the p-value for the greater than test? You can see the less than test on the screen, and what's the p-value for the greater than test? The less than test is in red. So the p-value for the greater than test is just going to be what adds to 1 because they're complements of each other. So what's going to be the p-value for the greater than test? Point exactly, just 1 minus. Great job, Zach, right there. Then what's the p-value for the does not equals test? The does not equals test, if we were to do the does not equals test, we'd have to go over here and put a result just as extreme. Then we'd have to shade the other side. And the does not equals test, we just take here and do that. So now for the does not equals test, great job, AJ, right there. We just times by 2. Does that make sense? And you can see the answer to the does not equals test right here. with the p-value being times by 2. And we're just taking our sample result and just doubling it on the other side. So I did it visually here, but it's also done for you on this slide here where you just double it on the other side. It's like a reflection of it. Great job, Zach, right there. 20 points. This is the practice we need. Just doing as many examples as we can do. And there are test questions just like this for finding p-values on the test. So now we get to the big part of this lecture. We've already done a little bit of this, but we have 4 steps to doing the test. And so when we do our statistical test, we start by writing our null and alternative hypothesis. What does the actual p-hat mean? So p-hat is the sample proportion. Oh, we're saying, so it says actual, which is kind of weird words right there. This is just what we observe in a sample. So this is our sample result right here. So it's, I almost think it's a misnomer. That's a great job right there, Leanne. 20 points, Leanne. I almost think it's a misnomer that it says actual right there. It's what you observe in your sample result. So the p-value is showing us the probability of our sample result or a result more extreme than it occurring by random chance given the null is true. And when you look at this, you can hear all those words as I say them. So the p-value is showing you the probability, which is this, of your sample result, which is this, or result more extreme, which is this. That's the probability of a result as extreme or more extreme than your sample result occurring by random chance variation, which is the curve itself, given the null is true. And that's why the null is at the center of the curve, because the null is the most likely thing to see if the null value is true. So you can see the null value right here, which we are assuming is true, or hypothesizing is true, is what we believe is true till we have evidence otherwise. And we're trying to see if it's less than 0.20 here. Does that make sense, Leanne? This is our sample result. So that's what we actually saw, I guess. So I would prefer just call it the sample result, because the probability of observing a sample result as extreme or more extreme than what we saw given the null is true. And so that's why the null goes at the center of the curve, because we're assuming the null is true according to the null hypothesis. We're saying, okay, this is the true proportion, so it should be at the center of the curve. That's what we should see if the null is true. We saw this. Well, how likely is this? And it's possible. We would not reject the null with this at a 0.05 alpha. We would say, I continue to believe it. And so now we're right here where we're going to actually do all the steps for a hypothesis test. And in this chapter, we do a test on the mean and we do a test on the proportion. So let's take a look at the test on the mean and the test on the proportion. Here we go. The first step is to write out that null and alternative hypothesis. And let's do 2 examples and see if you can do it. What would be the null hypothesis for Brian wants to see if the average GPA of UT students is greater than 3.5? Let's write this right here. And so here's the null. That'll help out. I'm going to delete this off so we have a little more room. I know I said, someone said, well, Brian, you said, you got to remember what I said about the null. Really? So the null hypothesis, Brian wants to test if the average GPA of students is greater, I can't trick Zach right there. And Zach, you're basically right. So the null hypothesis, Brian wants to test if UT students have a GPA greater than 3.5. Now, I'm actually stating something for the alternative right there. And so, Zach, for average, what are you going to put? You basically have it. And Zach knows the null has the equal sign. Even if I say I want to test this and I want you to show me the null has the equal sign. So no matter what, the null has the equal sign. But what should you put for average? What is going to be the parameter that we're testing? And remember, we talked about this earlier. We only have a few choices. And Zach, you are right, it's mu. So when we write out the null right here, we will pick one of these 3 in this class. There are more things you can pick. You can pick sigma, you can pick rho, you can pick beta. There's different things for different classes. These are the ones we do in our class. And then you will actually use the equal sign. And here's where you put whatever you're starting with. So let's write what Zach put right there and put it in for our null hypothesis. And we would put right here mu. So we need to insert a mu sign. Insert equation. Mu equals 3.5. How about this? Brian wants to test oh my gosh. to see if UT students, to see if more than 20% of UT students visit the T-Rec in a semester. Brian wants to test to see if more than 20% of UT students visit the T-Rec in a semester. So what would be the null? What would be the alternative? So Brian wants to test to see if more than 20% of UT students visit the T-Rex in a semester. And notice the question becomes, did you visit the T-Rex this semester? Did you visit the T-Rex? So what would we put here for this null hypothesis? So you also have to ask, are we doing proportions? Are we doing means? Are we doing two means? Let's write that out. And I think you're so close, Leanne. You're so close. And that's such a common mistake, Leanne and Zach and everyone. We're throwing 20 points. You're so close. You just forgot the parameter of interest. You're so close. And that's such a common mistake. A lot of people. And so what are you missing, Leanne? Here, I'll show you. Right now you have the following. And you're so close. You're just missing this right here. What should go right there? Like you just said the null, you have this right now, but you're missing a value right here. So which one are you going to put? Here, I'll show you the slide again. Zach, remember we're asking, do people go to the T-Rex? We asked someone to say, did you go to the T-Rex? And so think about these options right here. We have true mean, true proportion, or true difference between two means. Chase, this is awesome. Teamwork makes the dream work right here. Great job. We've put it all together. Layla, great job. I want people to know this. We have to get questions wrong during class. We got a new quote yesterday. Which quote is that, Mubot? We have a new quote yesterday, said during office hours, quote 83. And so it couldn't be more true. You have to get questions wrong during class to get them right on the exam. And so right here, we would put P because we're testing proportions. And once you see this, you're like, oh, wait a minute. We're asking, do you go to the T-Rex? Do you not go to the T-Rex? It's not a quantitative question. Like, we're not asking how much do you go to the T-Rex. I could change the question right here to say, Brian wants to test to see if students go to the T-Rex more than 5 visits per semester. And now we would change this back to mean. And the null hypothesis here, because we're seeing on average, do students go to it more than 5 visits? Because we'd have to go up to someone and ask them what question. While I write the null and alternative, what question would you ask somebody to collect data for this? What question would you ask somebody to collect data for this? And here would be the alternative. What question would you ask somebody to collect data? I want you to walk up to someone and ask them the question. And how would you ask them the question to collect data on this? Here's the null. We're making the alternative right here. How would you ask them the question to collect data for this? So Brian wants to test if students go to the T-Rex more than 5 visits per semester. His null hypothesis is that they go there on average 5 visits. His alternative is that they go there on average greater than the true mean. The true mean amount of times that students go to the T-Rex is greater than 5 visits. So how would you walk up to someone and collect data for this question? You'd simply ask them what? And just think about how that question sounds. So this question right here, which is means, how many times did you visit the T-Rex this semester? How many? Right there. Great job, Zach. That's how many, which is quantitative. But then this question right here, Brian wants to test if students go to the T-Rex. Brian wants to test if more than 20% of students go to the T-Rex. So with this, we'd have to ask somebody, did you go to the T-Rex this semester? Do you see the small difference right there? This question becomes, did you go to the T-Rex this semester? Because we're testing the proportion of students who go to the T-Rex, so it's a categorical question now. Did you go to the T-Rex this semester? And we're seeing if it's true that more than 20% of students go to the T-Rex. So the alternative right here would be the alternative of the proportion being greater than. So we'd ask, is it true that 20% of students go to the T-Rex, or do we have evidence that greater than 20% of students go to the T-Rex? Is there evidence for greater than 20%? So now we just need to do our test. And the test comes with assumptions. So when we do the statistical test right here, step number 2, we're going to do assumptions, and we'll talk about those assumptions here in a moment, but we're going to do a test. And I want you to look at this. The top part of every single test right here is just a what between two numbers. Every single test you will see in this class, whether it be this test I've highlighted right here, or another test we will look at here in a moment, every single test the top part of the test is just a difference. Every single test is just a difference. All you're seeing right here in the screen test right here is just a difference. And then we will take that difference and whatize it. We will take this difference and standardize it. If you remember from previous lectures, P times Q over N square root. What do you notice we assume that P naught is equal to? P naught is assumed to be equal to P. So since P naught is P, well then that basically makes this on the bottom right here, because we assume P naught is P. Well then this is basically P times Q over N square root. It's just the standard deviation again. We're taking this difference up top here and standardizing it, and we get a z-score, which is going to be known as a test statistic, which is a standardized difference. So the big step right here, step number 2, is to get your z-score. And we'll see this. We'll do an example here right before break. A big step right here is to get your z-score. From the z-score, we're then going to plot it to get the p-value here. So when we plot it to get the p-value, what are we doing? We're going to the normal curve and we're just plotting our sample results. And we take our sample result right here, plot it on the curve, and then we shade in the direction of the way it points. If you have a less than test, you will shade to the left. Well, that's way too big right there. If you have a less than test, you will shade to the left. And that's what you're seeing down here. If you have a greater or does not equals test, you will shade to both sides. I like to think of the does not equals test shading to both sides right there. The does not equals test shades both sides, and the greater than test will shade to the right. We don't have one on here, but we will see some today where we have a greater than test. And if we were to have the greater than test, you would shade to the right, and you'd get the following area over here, which would just be 1 minus the result down here. So if we had the greater than test, we would just shade the other direction on the curve. We would shade to the right of this result. The greater than test would shade to the right of it, and the less than test shades to the left of it. And then the p-value here would just be 1 minus the less than test. So last but not least, we are simply going to reject or not reject the null hypothesis. Reject or not reject. We're going to do an example here in just a second to see all these steps to where we go through and reject or not reject at the end. So let's go through and do a proportion test and then come back after break and do the means test. So here we go. Let's ask a question. There we go. What question would you like to ask UT students that is proportion related? What question would you like to ask UT students? Here, I'm going to start writing the thing. I want you to come up with a question we're going to ask UT students that's proportions related. It's going to be categorical. Don't do quantitative. So Brian goes out and talks to 100 random UT students and asks them, he finds out that 40 of them say yes. Is this good? He wants to see. What are we going to ask UT students? Then we have to see what we want to see. We might have more than 40 of them saying yes. And then we need to mark our notation for this. Let's go here. Step 1, null and alternative. Step 2, test results or test statistic. Step 3, p-value. Step 4, conclusion. So what are we going to go out and ask UT students? What question will we ask them? It has to be proportion related. And then we got to go through here and do the 4 steps. What should we ask UT students? It has to be proportion related. So we're going to ask 100 UT students this question. We're going to go up to them and say, do you think this? And what are we going to ask them? 100 UT students were asked the following question. And then we've got here the 4 steps. At the end of this, we'll either reject or not reject our null. So we'll have to write out the null alternative. So what are we going to ask UT students to begin with? Do you think there is enough student parking on campus? Oh, that's such a great question, Zach. Some 50 points right there. Do you think there is enough parking on campus? What do people say in the chat? Let's say let's do this. Let's do this. UT Parking believes, sorry, UT Parking, that students are happy with parking on campus. We want to show evidence that less than half of students are happy with parking. So Leila says no. We go out and talk to 100 UT students, random UT students, talk to 100 random UT students, and find out that 42 out of 100 say they are not happy. So, or say they are happy. There we go. Are happy. Is this good evidence to reject the null? Now, here's the problem. I hate parking. Haley says, parking is pretty tough. I know they try, but there's just a lot of things I don't understand. Like, here's what I think. If you get this is personal opinions. Gotta hit the button, right? Personal opinions with Brian. I think if you buy a parking space, personal opinions, that there should be a parking space for you. As in, they should not oversell. I think they oversell because not everyone's going to be parked on campus at the same time. I don't think that's the way it should go. I think if they have 5,000 spaces on campus, you sell 5,000 parking passes. And if they run out, that's the way it goes. And every semester, there's 5,000 parking passes because there's 5,000 spaces on campus. And yeah, and they probably need to like kind of maybe have something where they kind of, it's just personal opinions. I will say this, parking helped me out one time really big. So big thanks to parking. I know they got a tough job. Personal opinions with Brian right there. They've got a tough job. I wouldn't want to do their job because I've been at UT a long time and no one's ever liked parking. It's probably a lot. They like money. I doubt that, William. You can't say anything. No one likes money. Who likes money? Not me. I don't know. Actually, I think I'm one of the people who likes money the least. Just another real quick personal opinion with Brian. Money doesn't make you happy. I can just promise you that. As I've gotten older, I've gotten more money, and I'll tell you one of the things that's made me the least happy is COVID. Having more money during COVID definitely didn't make me happy. I wasn't like, oh man, I've got money. That makes me happy. Going out and doing things, being able to see your loved ones make you happy. And if there's anything the last year has taught us, it's not going to be money that makes you happy. It's those experiences, those times you get to spend. So make use of that. Tell the people you love that you love them, because money's not going to make you happy. I can just tell you that from living through COVID. It's not going to be money that makes you happy. Is this, you probably know that too. You probably, like, yeah, Brian, I experienced that too. Thank you, Sam, right there. Is there good reason to reject this null? Let's write out that null and alternative right here. Here we go by writing the null and alternative. What are we testing right here? We are testing to see if the true proportion, you just have to listen to yourself, because it's like, man, I wish I could just like go on a trip and to like Houston and see some things and do some stuff. It's like, I wish I could stare at an Airbnb. Like we've got more than enough money to stay at an Airbnb, but we're not doing that right now because, world. So it's not the money. It's like you can have all the money, but the money can just give you access to do stuff. Null has the equal sign. So we think money will make us happy till we get money. And then we're like, you know what? I feel about the same. They've done studies to show that when you get money, up to a certain amount, it changes your life. And then after a certain amount, it doesn't really change your life. Less than half. Can anyone help me out with the notation right here? This is going to be super important. Can anyone help me out with the notation before we go on break right here? That's the tough one. That's the hypothesized value. So the hypothesized value is usually the one people get wrong right here, or people forget about, because it's the new one for this chapter. What are the other values right here? And let me put the test down here, which will kind of help for us seeing the rest of the values. What are the other values on here? So be very careful. These are throwback questions. We'll go on break here in 5 minutes. 5-minute break in 5 minutes. The conditions are random, 10% is success failure. We'll talk more about conditions after break. They're just the classic conditions we use for proportions. But what are p hat exactly? And I think, so Zach went ahead, great job, Zach, right there. Zach went and took this, which is x, and found p hat. And this is n right here. So p hat is x over n. So x over n equals p hat. P hat is equal to 0.42. And so we get right here that 0.42 minus 0.50. And then we go down here and we have to do 0.50 times 0.50 over 100. And this will equal to our z-score. So what is the z equal to? I need this here. What is the z-score? So we've got all the notation right there. And so we've written out everything we want. We have all of our notation. And so we do p times q over n square root. And then this is 0.08 on top, negative. Oh, this is going to be interesting. Oh, wow. I didn't even mean for this to be this way. But this is going to be an interesting one. So now we have to find the p-value. And since this is a z-score, I need someone to help me out. Where do you think I should go to get the exact z-score? Since this is a z-score right here, I need someone to put a command in the chat to tell me where I should go to get the exact z-score. I'm going to draw it out right here and draw my guesstimate of it. And I need you to put, oh, great job, everyone right there. You know where to go. If we have a z-score and we want to plot it, we're going to go here to the David M. Lane applet. Mubot's telling us where to go. Can anyone tell me, and really great job, everyone. Thank you so much. I always worry that, especially to get close to break, that I'm going to lose everyone. Because I know it's like, oh, we need some break, Brian. We'll have break here in a second. We got it. We'll be done right at 10:35. So we got the David M. Lane. What is the z-score? What is the p-value going to be for this? It's going to be a little bit more than 5%. A little bit more than 5%, like 6.2%. I'll reap here. 6.2%, I say. So we want to go below. I say 6.2. Wait, that's wrong. Wait, below. Oh, negative. Ha ha. Ha ha. Oh, no, it's close. It's 5.4. I said 6.2. It's 5.5%. Rounded right there to 5.5. So the p-value right here is 5.5%. And so we go right here, and we just label this that the p-value is equal to 0.055. So with the p-value equal to 0.055, what are you going to do with your conclusion right here? With a p-value of 0.055, you are going to what? And this is the last step, and then we're done. We just did a false hypothesis test. So my p-value is what? My p-value, and this is key for your assignment, my p-value of 0.055 is greater than 0.05 alpha. Thus, I do not reject, or fail to reject is fine, reject the null hypothesis. This means the claim that 50% of students are happy with parking is what? Exactly, Sam is saying let it fly. This means the claim that 50% of students are happy with parking is believable. We do not reject the null. So it means the claim that 50% of students are happy with parking is believable. You might say, well, Brian, you only saw 42 out of 100 are happy with UT parking. Well, then it's possible that 50% are happy. I mean, we just took a random sample. Who's to say maybe another random sample would produce different results? What we saw is likely possible by random chance, given 50% is true. It wasn't that far away. Does that make sense to everybody? What we saw was likely by random chance. But what if, and this is a quick change I can do. Watch this very quick, because we got something really special right here. Now, p hat would be 0.35. We're going to break right after this. Now only 35 students said they were happy. So now you can see the quick change to mathematics we're doing, where we saw a new sample, just a different random sample, produced only 35% happy. And now the z-score is -3. And now, since we saw something more extreme, our p-value is going to get smaller. And we can even use the empirical rule to estimate it. So now we're down here on the curve, and the p-value now is equal to about 0.0015. That's from the empirical rule, the 68, 95, 99.7 rule. And now my p-value of this is less than this. Thus, I reject the null. This means that the claim of 50% is not believable. I have evidence the true proportion of students happy with parking is less than 50%. And that's got it. That's the alternative right here. And we have now rejected it. This is just a different example right here, where in this example right here, we had 35 students out of 100 happy. So that changed the p-hat, that changed the z-score, that changed the p-value, and then that changed the result. So we can see an example where we reject the null, and in the previous one, we did not reject the null. So hopefully you're understanding these 4 steps right here. Write the null and alternative, find the z-score, find the p-value, and then state your conclusion because the p-value is below alpha or the p-value is not below alpha. And that's got it just 2 minutes after where I wanted to go to, but I wanted to show a final example. I always like showing as many as we can. Let's hop to space. 5-minute break, start. Let's do this. What questions are there right now? Good work, everybody. Hopefully it makes sense how to do the 4 steps of testing. That's really all we covered right there. The whole point of the last hour and 20 minutes was to understand those 4 steps, to know how to write the null and alternative. Why are we doing it? Have you posted the videos for the project yet? Let me get the playlist going for that. You ready? Let's go grab the playlist. They're in different spots. Let's put together the playlist right here. And so we have decision trees. Let me go make... And so I'll send this. And let me go right here, new playlist. Mini project 2. Create. Okay. Reload page. And then let's add videos. Here we go, decision trees. Okay. I am putting videos on now. We are adding those videos. And then the second thing, we have a 1 sample t-test and a 2 sample t-test. And the 2 sample t-test will be tomorrow. I wish you could search your YouTube videos. Let's see what chat's saying. So Leanne, I am putting the videos on there right now, and I'll put the playlist in the chat. I've got so many videos on the channel. A lot of videos. Oh my gosh. Wow. Might be easier. Okay, so we got that. And then let's go to content. And here we go. Oh. 2 sample t-test. Here we go. Jump tutorials. Tabulate. Time plots. I know I made 2 sample t-test videos. Single mean, 2 means. Here we go. Okay. This will now have mini project. Mini project. Okay. I'm going to add some more videos to this. No, you're welcome, Leanne. Thank you for asking. I'm going to add some more videos to that. Let me send out an email reminder. So... some videos. Okay. And there it is. Link sent out. Yep. And I'll probably add... let me add one more video. We'll go 6-minute break. There we go. 2 sample T. Yep. What? Why do I have this published twice? Oh, I should have done that. I missed an opportunity. Okay, good. Maybe we'll talk about this at the end right here. Okay, so I've added more videos to it. Let me reorganize the videos a little bit here. 2 sample t-test comes at the end. And then we'll talk about this really quickly right here. Let me put decision trees. And I think I should do it. Let's stop this right on. Okay. Coming back here from break in 2 seconds. Oh my gosh. Streak's over. Streak is over. We're going for 6 minutes right there. Coming back from break right here. Let's go ahead and talk about the playlist right here and what's on the playlist. Okay, heading back right here. Let's do this. Let's head back over here to the main screen. Okay, so we have right here the project playlist. And you'll see you've got these tutorials right here, which are going to show you exactly what to do, exactly what to make. So if you're wondering, how do I make the output, which is sometimes the biggest hurdle for the project, is just go to the video and it'll show you exactly what you need to make. YouTube's been playing in lower def for me recently. Lower, is that only 720? Didn't record that. You've got here how to put your variables in for the decision tree. And you've got here how to make your tree. You've got the split history. Make sure to include your split history right here. So that's the split history of r squared increasing, which is the percent of variation in y explained by the variation in your variables in your tree. And last but not least, we should see there's the leaf report. So you can see you'll need to include the leaf report when making your project. You'll also need to include your split history when making the project. And you'll need to include a picture of your tree. You don't technically need this portion. That's the one portion you don't need. You will need the r squared and everything down here. So this is your tree. So take a picture of this. That's one picture. Picture of your tree. Second picture, picture of your split history. Third picture right here is going to be your picture of your leaf report down here on the bottom. So you can see the groups and what's inside of them. So that's one video right there on how to do the decision tree. The next video right here we have is on doing confidence intervals and tests on the mean, which is what we just were covering. So you'll see right here, we're doing the analyze distribution portion of it. Oh, I'm currently talking on this video. And so we have analyze and then distribution. With analyze distribution, we'll go here and we'll put in a quantitative variable as we were doing. We'll analyze that variable. We'll hit the stack just to make it look nice and neat. And then you can see over here, there is a confidence interval currently on the screen. We're analyzing the heights of UT students. So you can see a confidence interval right here. And instead of using that, we can use that one, or we can select a confidence interval of any value we want. So you can make a 90, 95, 99, or any other percent confidence interval you want. Then you'll put it in and you'll make it two-sided. And there you go. There's the confidence roll, 92%, just in case you want to make something other than a 95. Now, if you want to do the statistical test, you need to go to test mean, which is under the red arrow. The red arrow right there has all the options, the second one. And go to test mean. And with test mean, you'll enter in a hypothesized value. The hypothesized value you'll enter in is anything you choose. Don't go too crazy, but you could check with me if you want. But it's just a value that you hypothesize is true. And we'll do the z-test, so don't worry about putting in the t-test right there. We'll just use the z-test. And so Brian will enter in a value. He's hypothesizing that the true mean is equal to 69 inches tall. And so once we hypothesize this value, it'll run the statistical test, and you'll notice that is the does not equals test right there. That's the greater than test, and that is the less than test right there. And you can see the same relationship we talk about with the p-values, where the does not equals is double the smallest, and the less than and the greater than add up to 1. And there's our observed result down here, and there's the null hypothesized value that is true. So here is the test result, and you must include this. To be very clear, you need to include your confidence roll in some way, and you need to include your test results on here in some way to make sure I can see what you got. So please include the test results. So there is how to do the one sample t-test, and tomorrow we will be covering the two sample t-test. Categorical variable. Oh no, we just had a blip. Is everyone still here? Looks to have been a blip. The two sample t-test right here is going to take a categorical variable as an x and a quantitative variable as a y. And then we'll just go ahead and we can see the two groups right here. We're testing the difference in weights between males and females. And now we'll do the two sample t-test to see if there is a difference between the two groups. Awesome, Zach. Thank you so much. And this is testing, is there a true difference between the weights of males and females? And there are the results right there with the p-values and the observed difference of 48 pounds between males and females. Awesome. Well, with that, let's talk more. Jesse, thank you so much, everybody. For some reason, we get a random disconnect every once in a while. It hasn't happened for a while, but there's that random disconnect thing. Let's hop back over and keep talking about statistical tests. Here we go. So with statistical tests, we talked a little bit about the project. Project playlist is in the chat. It's emailed out right now. If you have questions, let me know. So with hypothesis test for the mean, what kind of data are we working with? Are we working with quantitative or categorical data? When we test the mean, which means we'd start with something like, video is a little blurry though, so I don't know about the connection. Go down there and click the HD. Jesse, thank you so much for saying that. That can happen every once in a while. There should be a button over on the other side of the screen that has a scroll wheel, and it should let you change it to HD. For some reason, it'll downgrade quality every once in a while. And Zach is correct right there. So there's a little scroll wheel button. So we made that message when I'm not in HD. And a lot of times, for some reason, when YouTube does that disconnect, reconnect thing, it'll change the video quality. And then you can up the video quality back to HD. I don't know. One of these days, maybe we'll just switch to Twitch, because I don't know if Twitch has these random issues too, but streaming platforms sometimes have weird issues. But yeah. So thank you for pointing that out, Jesse. Let's throw some 50 points right there. So with this, we are testing a quantitative value when we test the mean. And not much is going to change right here. All we're going to do now is switch our null hypothesis to doing the null states that the true mean is equal to some hypothesized mean. And then we're going to do a difference standardized. So when I write this question, I'm going to have to give you some hypothesized value to start out that's quantitative to start. And when we do a one sample t-test, we will always do n-1 degrees of freedom, just like a one sample t confidence interval. So both of these have n-1 degrees of freedom. So let's go ahead and look at one of these tests right here. Now we're going to go out and test to see what quantity of Mirex is in fish. Exciting stuff right here. This value here in notation is what? And I think this is what people forget. Take a moment. Let's throw some 50 points if people get this. This value Brian is highlighting is what in notation. And I think I can copy this into chat so you can use this. So go ahead and use this if you want to use mu right. Oh, it says M. It won't let us put mu in chat. It copied as M. Can I grab a mu symbol? What value has Brian highlighted in notation right there? There we go. There's a mu. What value has Brian highlighted? Not the one I've right there. That's mu. What is this value right here? What is that value right there in notation? And that's the one people always forget. The answer is on the previous slide, but it's the value we are hypothesizing is true according to the null hypothesis. So we're saying, I believe this is currently true till I have evidence. I'm looking for evidence that the true mean value of murex in fish is greater than this quantity. So what value am I hypothesizing is true right now? What value what is the notation for it? I'm hypothesizing 0.08 is true. So that means this is equal to what value? Close, Zach, close. That's not the population mean, that's the hypothesized population mean. So mu naught is equal to this right here. Because what we're stating to start is that the true mean, which is the population mean, is equal to some hypothesized value. And that's also what will go right here. So that's important to know the notation. So whatever we hypothesize is true will go right here. Does that make sense? So we're saying I hypothesize that the true mean is equal to some hypothesized value, and then that's the value we are going to test right here. So it's important to know when you see this right here, that is mu naught. Now we're saying the true mean is equal to this. So it's also still, it's kind of the population mean. It's what we believe the population mean is. It's what we hypothesize the population mean is. So it's mu naught. It's the hypothesized value of the population mean to start out here for the problem. Good stuff right there. So when we run this problem, we need to get some sort of result from this that would lead us to reject or not reject the null. So imagine if we have a little fish right here. And this fish, it's going to be the worst fish ever. I don't know, not horrible. It's just dripping with murex. I have no idea what murex is, but it doesn't sound like something good to me that you want on the fish. So the fish, we just pull it out and it's dripping with murex. Well, then we would reject the null and be like, that's not even parts per million. That's like parts per fish. Like, this is ridiculous. We reject the null. But what if there was like none on it? Well, then we'd probably not reject the null because we wouldn't have evidence that the true amount on it, on the fish, is greater than 0.08 parts per million because we're not even seeing any on the fish. So we need to think about how this looks and start by looking at the conditions. Condition 1 is that the fish we select must be random. So with selecting the fish at random, we're just going to take random fish. We're not going to select the fish that are closest to us or the fish that are swimming near the murex. We're going to take random fish. Condition 2 is that we take what percent of the fish. Condition 1 is we always take things randomly. Condition 2 is going to be we take fish what? And I'll pull up something here to help. So condition 1 is that we take random fish. Condition 2 is that we what? Condition 1 is that we take random fish. And then condition 2 is that we take what? Condition 1 is that we take random fish. And then condition 2, less than 10% of all fish. Exactly, less than 10% of all fish. So we must remember our conditions. Now, what do you think with taking the fish, the third condition will be? What do you think the third condition will be with taking the fish? What will be the third condition with taking the fish? Any ideas on what that third condition will be? So the fish, the murex on the fish is a quantitative thing. We're asking how much murex. Exactly, Sam. Great job, Sam. And Zach also. It's nearly normal / large enough n. Technically, and I always hate that we call this two different names. That's why I combined it right there. It's going to technically be the nearly normal. Large enough n is only for sampling distribution. So the large enough n is only for the sampling distribution of the sample mean. So the nearly normal is for quantitative, like one sample t, two sample t, interval or test. So this is for the t-test. So I'll just put like a t right here. For t-test, t-interval, all the t stuff, the nearly normal is. Personally, and I've always told my students, there's just one or two random questions that might mention this on the test. You should know that large enough n is for sampling distributions and nearly normal is for t distributions. but both of these are for quantitative data. That's why I put them together. I've never had a problem if people just change the names of them because they're both just asking if the distribution is normal based on, do we have a large enough sample? Does it look normal? We're just asking, how does it look? So with that being the third condition, does that look good enough to you? We've collected data on 150 fish. Does this look kind of normal enough to you? We'll do a nice color on this. Does that look extremely skewed or maybe a little bit skewed? What do you think? Does that look good enough? And that's all we're asking. And you can tell that it's right skewed because the mean is higher than the median. So it is the right skewed. Little Monster Man's got a little bit of a tail to him right there. How does that look to you? Good enough or no, not good enough? Condition 1 was random. Condition 2 was less than 10% of all fish are taken. And condition 3 is nearly normal, large enough n. And does that look nearly normal to you? And we're using nearly normal because we're doing the t-test. Does that look nearly normal to you? I'd say good enough. I'd say good enough. A little bit of a skew right there, not too much. And since it's only a little bit skewed, we don't need that large of a sample size. Now that does make it sound like large enough n, but that's why the two are so similar. It's like they're kind of the same condition-ish. So we're good on all the conditions. So all we do now is plug in the numbers. Which step is this? Plugging in the numbers is which step of our hypothesis testing. This is the one we just did a moment ago. So when we're plugging in the numbers and getting a t-score or a z-score, that is which step of doing your hypothesis testing. Plugging in your numbers to find the t or the z-score. The test statistic is test step 2. Great job, Chase, right there. Let's throw some 20 points out to the chat. It is step number 2 where we get the t or the z. So now once we get the t or the z, we're simply going to find the what next. So what are you going to see in the notes? Once we get the t or the z, we get the standardized value. What are we going to find next? We just found the t or the z. We found the t, technically. This is a t-score because we're doing means. Mr. T is mean if you're doing drugs. So Mr. T, mean. What are we going to find next that we just found the t-score, which is our standardized result? We're going to find the p-value. There you go. Boom, p-value. And now that we found the p-value, guess what we're going to do? We're going to reject or not reject the null. And look at the p-value. The p-value here for a t with 149 degrees of freedom, remember, the sample size, there's your daily pen drop, the sample size was equal to 150. The degrees of freedom are equal to 149. And so this is a t with 149 degrees of freedom. And we're looking at greater than 2.8004. And that's an area that's very small. That's the area right here above the curve. And so we're looking at less than 0.2%. So what are we going to do? Are we going to continue to believe the null or reject the null? The p-value is low, so what do? Since the p-value there is very, very, very low, you are going to reject the null. With the p-value exactly Sam, exactly Quicksilver, we're going to reject the null. The p-value is low, we reject the null. We have evidence for the alternative that the true mean quantity of Murex in the fish is greater than 0.08 parts per million. So you can see how we do this in Jump right here, which we've looked at a little bit today also. You'll see the same exact result. And here's what I was drawing just a moment ago. I was drawing this value right here of the greater than. And you can see right there. And this is just how to do everything in Jump, which we have the videos sent out for right now. All of this good stuff right here. And there's class activities. And I think that might be it. Intervals and tests. Yes, we must do this. So that's it for the tests, but you know what? Let's do an example test right here, an example t-test, and let's ask a question. So someone come up with a question. Let's do this. Let's hop to the main screen. Because this is, the next part's also on the project, and then we get to start a little bit chapter 16 today. Okay. Brian goes out and asks UT students what? I want a quantitative question. Let's put things here. So what's Brian going to ask UT students? Step 1. Null and alternative. Ah, that's what we're going to see right here, Chase. Great question. We're going to see, so this is test statistic. This is where we're going to calculate the t, the z, or the chi-squared. More on that on Thursday. And step 3, so what are we going to ask UT students? And then we'll calculate a t right here, Chase. So really great question. P-value, step 4. reject or not reject, or fail to reject. So what are we going to ask? What are we going to ask UT students? Brian goes out and asks UT students what? What am I going to go out and ask the UT students? I can ask them any quantitative question. Now, I could ask them any question, but let's go with a quantitative question. Brian goes out and asks 100 random UT students. I always use 100. It's just a nice, neat number. You can use any number you want, though. Brian goes out and asks 100 random UT students what? It needs to be a quantitative question. So it needs to be something quantitative that we can do the mean of. How many parking tickets have you gotten? So what's interesting is parking tickets, Zach, might be very, very, very right skew. But we do have a sample size of 100, which means we probably have enough that it would be nearly normal. How many credit hours are you taking? Let's see. We could do, let's see, we'll do credit hours. So Zach and Leanne, thank you so much. So random UT students, how many credit hours, and exactly GPA credit hours. These are all quantitative questions, which we can do for this example. Great job, Chase. Excellent work there. How many credit hours are you taking this semester? He believes currently that students take 15 hours. That's what, most students take on average. Is there evidence against this claim? He finds in a sample a mean of 16.5 with a standard deviation of 3 hours. Okay. So here is the mean in a sample. Take a moment. What is it not like grammar-wise there? How many credit hours you are taking? And let's mark the notation. Who can tell us the values in the notation right here? So you see 100, 15, 16.5, and 3. There's one of these that is the hard one everyone always forgets, and this is going to help us lead to answer Chase's question about finding that T or Z here in a moment. But we need to first mark the notation. Whenever you see a problem, mark the notation. I've had people get to problems and be like, I can't solve this. I don't have all the notation. I say, double check. You might have something mismarked. They're like, no, I think it's an error. And they're like, I don't have the standard deviation or something. I'm like, well, look at the notation. I'm like, I promise you, I'll look over it and I'll be like, yep, it's correct problem. This one's a little bit easier to see where the standard deviation is. I'll be like, Mark, make sure everything's marked correctly. So what do we have? Go ahead and put one of them. Just try putting one of them. I'll circle them. We'll put some arrows up. So try that's the tough one right there. That's one usually people get wrong or just forget how to do because it's the new one for this chapter. So what are some of these right here? And this will help when we go to the equations. The better we get with marking our notation, the better we get when we get to the equations. We're like, oh, this goes here, this goes here, this goes here. Solve the equation, solve for the t statistic. So I'll go ahead and write the t statistic formula down here. I think you've got, oh, close, Zach, close. So you've mixed notation. P hat is sample proportion. So P hat is sample proportion. This is why we practice, because there's just one error right there. So, and you probably would catch it. You might not have that big of an error, but there's the formula we're going to use. Yep, you're seeing it. There you go. And it's just very common. That's why I want everyone to always practice doing the notation, and then you catch little things like that, because that's the sample mean. That's the sample standard deviation. The null value, the null mean, is this right here. That's the hypothesized true mean, and then that's the sample size. And it's just the practice when you start seeing it that this is the sample mean, this is the sample standard deviation, this is the hypothesized true mean, this is the sample size. So the more you practice, better you get, and then you're like, got it. I don't think people realize that I just want to say this, the people who do really well on the tests, you have to get so many questions wrong. You have to just get questions wrong till you start getting them correct. And you don't want to be that first time you get questions wrong to be on the test. You want to be in class where you're like, oh, I got it wrong. And then you're like, okay, that's this. And then you get it right. You're like, got it down. That's where you find your knowledge gaps. That's what we're here to do. Find those knowledge gaps and just pave over them with knowledge. So we got the null hypothesis. The null always has the equal sign. So the null has the equal sign. Now here's a confusing thing. While I write this out, I want you to tell me what sign is going to go right here. So look at what claim Brian is making. He believes currently students are taking... Brian believes this is true currently. So what sign are we going to use right here? Because we're going to look at the question to figure out the sign of the alternative. So what sign is Brian going to use right there? What sign is Brian going to use right there? That's the null value right there. And all we do is we change the sign. So Brian believes currently that students take 15 hours. He wants to see if there's evidence against this. So Brian believes currently students take 15 hours. He wants to see if this is true or not true. So he really didn't tell you which direction. He just wants to see if it's true that students take 15 hours. He currently believes that, and he wants to see if it's true. William, great job right there. We're going to use does not equals. That's one of the hardest ones to identify because it doesn't really give you a preference. So if you don't see a strong preference either way, you're talking about the does not equals sign right there. So the does not equals is when we just say, is this true or is this not true? You know, we're testing to see if students take 15 hours. Exactly. So now we're going to plug in the numbers right here. And this is where Chase was asking about how do we get the t-score? The t-score is where we take our observed value of 16.5 minus the hypothesized value, divide that by 3, which is the standard deviation, over the square root of 100. Now, I was really nice to myself because I made it so I got numbers I know how to work with. This is 3 over 10, and this is going to equal to what? It's going to equal to 5. So if you are doing the same work I'm doing right here, I believe this should be equal to 5. If someone can put yes or no in the chat, that'd be awesome. But 3/10 right there, that's 1.5 over 0.3, which is going to be 5. So we should get a t-statistic of 5. Ooh, I will throw 50 points out if someone tells me the one thing I forgot to do right here, which, I mean, I'm remembering it right now, but there's one other bit of notation I forgot. I'm going to pause here on the screen. So thank you so much, William, right there. I'm going to pause here on the screen, and I'm going to bring something up. Can anyone tell me the one bit of notation I forgot? It's not the end of the world. We need it right now because we're about to go and get something. But I forgot to get something. And so hopefully, Chase, tell me if that made sense when I found the t-statistic right there. So I'm going to bring this up. What is the one bit of notation I forgot? I forgot one thing. One bit of notation. The degrees of freedom, exactly. So the degrees of freedom for this tell us what t-distribution we're using, and it's n minus 1 right now for a one sample t. Just remember one sample t, n minus 1. So we have the one sample t, n minus 1, and we go over here with 99 degrees of freedom. A t-score of 5. Yes, Chase. Awesome work, Chase. And what does anyone think? What do you think the p-value? I want you to look at this before I put in 5 for the t-statistic. What do you think the p-value will be basically equal to with a t of 5? This would be a fair test question. And you just look at the graphic and just be like, it's about this. You can type it very quickly. When I put the t of 5 in right here, and I wish I could block out the p-value. So just think with the t of 5, and we're doing the greater than, because we're going to put 5 in and it'll graph greater than that. That's not 5. But what do you think the t-statistic will be equal to when I do a t of 5? So we're going to graph greater than 5. And I'll show you what it would look like visually. Yep, Zach. Yep. So we're going to go right here. And we're basically off the curve. We're over here at a t of 5. And we're graphing greater than it, which is basically a p-value of about 0. It's close to. You could carry it out. There's a lot of ways we can get the decimals on this. A lot of statistical programs like the one I use will give you the exact p-value. Like, let's say you were really interested in getting that p-value. Like, let's say you're like, Brian, I don't like putting 0 as my p-value because the result is possible. Like, we would say, you know, it's possible, but it's very, very unlikely. So we'd go over here, and we would go here to QT5, no, PT. Wait, what? Oh, degrees of freedom. Losing my mind. Okay, then it's 1 minus. Okay, so there it is right here. There's the p-value right here. The probability of something greater than 5 with 99 degrees of freedom. And you can see it's 0.00000 and then 1, 2 or so. So there it is in scientific notation. It's just so small that these applets will often say 0 for it right behind me right here. So you can't even see it because it's off the curve where 5 is at. And it's it's ridiculously small. Like the applet's just basically saying to you that's a p-value of 0. But if you really wanted, there are ways to calculate it, and there is the calculation in scientific notation. So we do have ways of getting it, but for all intents and purposes, every statistician is going to look at this and say that's about 0. Since it's about 0, what are you going to do right here? Your p-value is either low or high. When the p-value is low, reject the null. When the p-value is high, just let it fly. So what are you going to do right here? My p-value of basically 0 is well below 0.05. I reject the null hypothesis that students take 15 hours. I have evidence that the hours they take are different than 15 hours, or is not equal to 15 hours. Does this make sense right here? Because our p-value is low, we reject the null. With our p-value being low, we reject the null, and we have evidence for the alternative that the truth is not equal to 15 hours. So this is another example right here of the 4 steps to hypothesis test. Very, very important stuff right here with the 4 steps. And let's do the last bit of this chapter right here, going through intervals and tests. So we've actually been doing the same thing. An interval and a test will come to the same conclusion. If I were to tell you about the new Nintendo system coming out, oh man, I'd love that. Nintendo Switch is awesome, but let's say the new Nintendo system is going to cost between $400 to $600. What would you say? Well, first off, quick question. What is the margin of error for this interval? So everyone usually can calculate this one really quickly because they can see it. Once you see it here, you're like, oh, the margin of error is plus or minus this right here. And then we should know how to get it, that it's the upper minus the lower divided by 2. There's test questions that do this. We have test questions that calculate the margin of error. $100 exactly. The margin of error here is $100. And it's just the upper minus lower divided by 2 to get the margin of error of an interval. And great job, Jesse and Zach, right there. So then what if I told you Brian currently believes that the true price in stores, the average price we will see for the new Nintendo system is going to be $900. And the alternative is that the average price is not going to be $900. What would you do with Brian's belief with this interval? Great job, Valinus, right there. What would you do with this $900 claim? Because Brian is claiming $900. That is Brian's null hypothesis. What would you do with Brian's null hypothesis? So what would you do with Brian's null hypothesis right here? Brian believes $900, but you have an interval estimating the truth is somewhere to $400, $600. Brian's null hypothesis would be what with that interval? Which you can use the interval to do this. With that interval, and this is part of your project, you can look at a null value and see if it is what. You can reject it because that value is what to the interval. We can reject that value because it's outside the interval. Does that make sense? We can reject this value because it's out. Trash Williams says, I agree. Trash that value. Go away. We're rejecting that value. But what's really interesting is could you reject this value right here? Could you reject that value? If we hypothesize that 600 is true, could we reject this or not reject? Now be very careful. It's on the fence. It's literally on the fence. That means it's on your property line. If it's on the fence, it's your property line still. So it's on the fence. It's not over the fence. It's not over the fence. It's on it. Which you're like, what? You shouldn't be on the fence. We can't reject it. So anything on the bounds of the interval, within or touching the interval, is something we could believe. So at this point, we would continue to believe, would say, yeah, $600 is possible. So we cannot reject this. Great job there. So confidence intervals and tests do the same thing. We can approximate a hypothesis test with a confidence interval just by looking to see if the value is in the interval or the value is not in the interval. And I want you to look at this. If you make a 95% confidence interval, that is a same sort of thing as a two-tailed test with what alpha level? A 95% confidence interval is going to be mechanically the same as a two-tailed test with what confidence level? A 95% confidence interval is the same as a two-tailed does not equals test. So this is the does not equals test, which means it's two-sided. The does not equals two-sided test, it's the same thing, 95% confidence. Well, then you're just saying, well, then let's use, this is 95% confidence interval. And then this right here means we're just using an alpha on the two-tailed test, which is the percent of time we reject. It's the same thing as saying I would reject this using a blank alpha on a two-tailed test, 5% alpha. And so you can do 0.05. A lot of times we mention alpha as 0.05, but people do call it like a 5% alpha. So, which it does say on the slide right there, or 0.05 alpha or 5% alpha means the same thing because decimals are percentages. And we can see this result right here, where notice, on the two-tailed test, we have a p-value of 0.0379. And the next slide is really confusing, but I want to make sure. So if the test mean falls outside the confidence interval, we reject the null, correct. So if the tested value falls outside the confidence interval, we would reject it. Now I want you to tell me, would this value be inside of a 95% confidence interval? So I want to look at a 95% first. Would this value right here be inside or outside a 95% confidence interval? And I want you to think, can you reject this at the 0.05 level? Can you reject this at the 0.05 level of significance? Can you, first off, can you reject that? Say I can or cannot. At the 0.05 level, which means, is this below 0.05? All we're saying is this p-value here below 0.05? And that means we can or cannot reject it. So to say, can I reject this at the 0.05 level of significance says, is this p-value below 0.05? And if it is, then we can reject it at the 0.05 level of significance. Because we're just saying it would occur by random chance. We can. Does that make sense? We can reject this. So will this value be inside? Because we can reject it. I just want you to keep that in your head. To go back to here, it would look visually, I've got the one we can't reject. It'd be over here. So we can reject it. So that means this value will be what to a 95% confidence interval? So since we can reject it, so if we can reject it, the value will be what? Just look at this example right here. Since we can reject it, with a 95% confidence interval, the value will be what? Outside. Let's take a look. Here's the 95% confidence interval right here. Only look at this one. Do you see 33? Here's the value. And here's the confidence interval. The value is what to the confidence interval right now? You can see it. The value is where it's just barely, but be careful. This is still, ooh, we're moving everything around. It's just barely. Don't get confused by it. This value right here, is it inside or outside that confidence interval? Is it inside of it or is it outside of it? Just like you were saying a moment ago, that value right there is outside the confidence interval. Let's go down to the extreme example though. What if we were to make a 97% confidence interval? A 97% confidence interval would be using an alpha level to test this at what? What would be the alpha level at a 97%? And it is on the screen. At a 97% confidence interval, we'd be using a what alpha level to test this? 97% confidence, what alpha level is being used right here to test this? 97% confidence would relate to you doing a two-tailed test with the 0.03 alpha level. Now I want you to say, is this value, can we reject or not reject? So you can say can or just say cannot. So can we reject this at the 0.03 level of significance? We can or cannot reject that. So at the 0.03 level, and you have to look to say, is this above or below this? Because remember, when the p-value is lower than alpha, we reject. When the p-value is higher, we... So at the 0.03 level, can we reject or not reject? At the 0.03 level, can we reject or not reject? So at the 0.03, we cannot reject. That means since we cannot reject it at the 0.03 level, it will be what to a 97% confidence interval? It'll be in or outside of, just an in or out. In, out. In or out of a 97% confidence interval, since we cannot reject it. We cannot reject it, that'll mean it's what to the interval. If at the point, it'll be inside. And let's take a look. With the 97% confidence interval, which is the bottom one down here, the 97% confidence interval, there's the interval, and here's the value. Now, it's just barely inside, but that's fine. It's inside the interval. The value is now inside the interval. This is a test. Yeah. I promise you, these things appear. This is on Canvas content. These are on the tests. And so the value is inside the confidence interval. And since the value is inside the confidence interval, we cannot reject it at the 0.03 level of significance. So if we did a test here, a two-tailed test with 0.03 alpha, cannot reject because it's inside. But up here at top, at the 0.05 level of significance, we can reject. We would reject that value. So we'd reject it at the 0.05 level of significance. We cannot reject at the 0.03 level of significance. So we can see how these relate right here, and it just goes through and shows it. And just more examples right here showing the same thing. I think we're just to class exercises because I was like, we really only have one more thing. P-values, what does it tell us? Oh, yes. We've been talking about this a lot today, but what about the p-value right here? I think that's it for these notes. Just p-value and more examples. So we're going to do more examples. And I don't know if we'll start the next chapter. I might not start it because it's a shorter chapter, but I don't want to go too quickly through material. The p-value right here is basically our evidence. And I've been talking about this alpha thing today. Alpha is just a value you pick. When we talk about alpha right here, we're just talking about a limbo bar. And the alpha is usually set to 0.05. But you can pick where to set alpha. Is Brian, by lowering his alpha, making it easier or harder to reject? When Brian sets his alpha to 0.01, Brian has now made it what to reject the null. By setting your alpha to 0.01, because we have to have a p-value lower than alpha, remember when the p-value is high, just let it fly. So here's when it's high, we just let the null fly. When the p-value is low, reject the null. So am I making it harder to reject? Because it's like you got a limbo under it. You got to be like, okay, limbo time here. So we're trying to get underneath this bar and limbo underneath it, and it's much harder to limbo under the bar. We might not be able to get sample results that are far enough away to show good evidence to reject the null. And we'll see this especially in the next chapter, that you can do this. I should have put the limbo bar at a different spot. But you can, that might be where 0.05 is at, you can raise the limbo bar. And this is a tricky, now it's much easier to reject the null because we're just saying we will reject p-values below 0.10. This is all alpha is. It's just saying, when do you reject the null? Does that make sense to everybody? Alpha is just saying, when do I reject the null? Right now, I want you to put this in the chat. Right now, Brian will reject the null when he gets... Brian will reject the null. Finish this sentence right here. Brian will reject the null when he gets what's that are what right here. Using this, Brian will reject the null when he gets what's that are what. Because that's what alpha tells me. All I need to see in my results, because I can use an alpha of 0.10 if I want. It's not good statistics. We usually use 0.05. It's just what a lot of disciplines use. You'll hear 0.05 alpha everywhere. But I could switch my alpha. And now Brian will reject the null if he gets If he gets what? I can reject the null anytime I get what? Because think right here. Brian will reject null when he gets p-values below 0.10. Exactly. That's exactly it. And that's all alpha is. Brian will reject the null when Brian gets p-values less than 0.99. What do you think about that? Is that good statistics? Brian will reject the null when he gets p-values less than 0.99. We'll see this in the next chapter. Sounds to me like Brian's rejecting the null too much. Brian will reject the null when Brian gets p-values less than this right here. Would you say Brian has very high or low standards right here? Now it's going to look kind of reverse, but Brian's standards right now would be very, this is very, very what standards? Very high standards. I know you're saying, well, isn't the p-value there, or isn't the alpha low? We're saying we require a lot of evidence. This is a very high standard. You're saying you need tons of evidence to reject the null, because the lower the p-value is, the more evidence. And now Brian's got to somehow break reality to get underneath that. That's very high standards to have a low alpha level. Almost misspoke there. But the alpha level is the requirement for p-values to reject the null. When the p-values are lower, you reject. And when the p-values are higher, you fail to reject. So really, this is fail to reject right here. You can just move it around. You better watch out though. This is, I'm like, someone's gonna like clip that and be like, Brian says you can just make your alpha whatever you want. It's bad statistics. What do we usually, if no one tells you what alpha is, what would you assume alpha is if no one told you what alpha is? If no one said anything to you about alpha for a problem and you were just doing reject or do not reject the null for any class of 0.05. That's just, you just assume that. It's classic statistics. It's what everyone does, unless someone says we're using an alpha of this. And what would you do if you went to a laboratory and they told you they're using an alpha? Oh gosh, I've seen things like that. I've seen things like this. You might say, you're making it to what to find results right now? You're making it to what to reject the null? If they used an alpha of this right here and you went to a lab, you might say, I know I'm the new person here, but you're kind of making it to this to reject the null. You're making it too easy. You're kind of, maybe you're finding you're making too many type 1 errors. More on that in chapter 16. But yeah, I think it's just the notes right here. It's just the cutoff for making decisions. And then just some examples. Example problem right here. What do people want to do? That's just another example problem, and we like to do our own because I always figure you can read the notes. It just goes through more example problems, shows you how to find Z statistics and T statistics, but we like to do as many as we can, and I like to go beyond the notes. That way you have things outside of the notes. I'm not just always reading notes. Would people like, right now, we'll start doing my Pearson at 11:40. Would you like to talk about, would you like an example problem? What would you like? Tell me what you'd like in the chat right now. You're here. You get to pick what you want. We could go right to my Pearson if you want, start doing my Pearson problems. We should be able to do chapter 16 and 17 tomorrow. Homework, William says. That might win out, William, right there. We'll see what a few more people vote. Put on a little music right here. So put your votes in what you want to do. And that's chapter 15. That's one of the last big chapters. Because chapter 16 is much shorter. I'm not going to do chapter 16 right now. It's much, much shorter. The interpreting p-values is like a review. Here's the 0.05 threshold again. There's like everything's homework. We could do the 2 sample test, or are we doing that tomorrow? Tomorrow. But I can give you some videos on that, Leanne, if you want. And please send me your work. If you're like, hey, Brian, can you review this? I want to get it in for bonus. So send it to me if you want, Leanne. You know what? Let's talk about I'm just going to talk about that right now. So let me talk about it, and I will explain it, and then we'll do homework. So we're going to show a 2 sample t-test, and then we're going to do homework. So Leanne, here we go. Let's show the 2 sample t-test. Okay, so thank you to everyone who's doing the project early. So this goes out to you right here. If you're doing the project early, let's talk about a 2 sample t-test. The only difference between a 1 sample and a 2 sample t-test is a 2 sample t-test is going to have 2 groups. So that's what a 2 sample t-test means. Like we can test the difference here between, let's say, and I think we got to do something. Let's do political stuff for once in this world. Let's test the difference between liberals and conservatives. Now, you'll notice I'm narrowing this down to 2 groups. You don't have to do this for your project. I'm just doing something that I wouldn't expect people to do. And I'm removing out the moderates. We're only going to do liberals versus conservatives. And now to do a 2 sample t-test, so we have 2 groups. Does that make sense why it's a 2 sample t-test? The 2 sample t-test means there's what? Put it in the chat right now. 2 sample t-test means we're testing 2 whats. Like the differences between 2 whats. And since it's a t-test, Mr. T is mean, we're going to test a quantitative variable. Let's see who has more friends. Ooh. Liberals versus conservatives. I have no idea how this is going to go. Don't worry. Listen to each other. Talk to each other. We're just seeing who has more friends right here. Liberals or conservatives. We'll find out. Is there a difference? Is there not a difference? I don't know. And we're testing the difference between 2 groups on a quantitative value. Does that make sense? It's a t-test, so it's means. And we're testing the difference between 2 groups. And let's go here and take political beliefs, which we narrowed down to 2 groups. And what do you notice? We got the 2 groups right here. And let's see who has more friends. So here's how to do the test. The test, if you didn't see, I'll show it again, was analyze fit y by x. So we're going to do a 2 variable test, analyze fit y by x. We're going to go right here to Facebook friends and put that in as the y variable. And then we're going to go to political beliefs. I did turn this into a 2 variable thing, so you can't do this unless you eliminate like I did. And so this is a two-group variable, and we have a quantitative y that we're analyzing for a t-test. Now we have the two groups, conservative versus liberal. And let's go here. See, we excluded those rows. And let's go here to the t-test. The t-test is going to do the two-sample t-test. And here's the results. And the result is very, very statistically significant. And which group has more friends? This is old data, though, so maybe things have changed. Who here can tell us who had more friends in this group? You can kind of see it. Now, don't do this output, but you can really see it if you do this. I'll remove this output here in a moment. Makes it a little bit easy to see who had more friends, because this is now showing you the means. In this data we had of students, who on average had more Facebook friends? Pretty easy to see visually now, which is nice to get the visuals. What do we see right here? Which of the groups had more friends? Exactly, conservatives. And so we go right here, and let's go right here, remove that output. And how could I know this right here? If you notice, it says liberal minus conservative. Do you notice how this is a negative difference right here? This difference here is negative. So since the difference here is negative, that means conservative had a higher average. Does that make sense to everybody right here? Liberal minus conservative. Conservative had a higher average because we're doing the average amount of friends liberals had minus the average amount of friends conservative had. It's like 5 minus 10 is a negative number, so the second number was bigger. So on average, conservatives had 180.85 more friends than liberals for Facebook friends. And is this difference statistically significant? The answer is most definitely yes. That was my internet provider. Okay. I thought they were saying something about the internet. The answer is most definitely yes. And do you see this? This is the alternative hypothesis right here. And this is the output you'll be interpreting. This is the output that you need to put on your project. And I'm basically going to interpret this. And I hope everyone doesn't do this. I might see like everyone doing this output. We see right here a difference between liberals and conservatives, where conservatives had on average 180.85 more Facebook friends than liberals. This difference is statistically significant when we test to see if there is a difference. And this is because the p-value of 0.00001 is well below 0.05. And this is for the does not equals test, where I'm testing the null hypothesis of the true difference between the means is equal to 0. And the alternative would be that the true difference between the means is not equal to 0. Does this, Leanne, does this help right here? We're going to do some My Pearson here in a second, but does this make more sense? Do people feel like they could possibly, like for the project, are you feeling like you can do a two-sample t-test? And then we're going to go over this more in depth tomorrow. This is the t statistic right here, which is actually just these two numbers divided. If you were to take this number and divide by this number, you would get the t statistic right there, which is just the difference between the two sample means over it. Yeah. Email me questions if you have it. That's a good reason why it's bonus right now, because, again, and that's the standard error of the difference. And this will be equal to the t. And understanding this output is very important right here. Can we do the box plot over the dot, over this? Yeah, you probably could. Yeah, if you want to see that right here, let's go take a look at that. Let me zoom back out here. And you're saying, can we do the box plot over the dot plot? Yeah, you should. I think if you do this, yeah, you can go to quantiles. There you go right there. Yeah, it's not a bad idea. You can include then the output too if you want. It's a little bit easier to see. This does show median right here. But median is kind of following it. You could include this right here. Makes it a little bit easier to see. Yeah, definitely. Good to see that right there. And you can analyze. I don't analyze the medians, but do you notice how conservatives have a higher median? So got that right there. We could test any sort of variable. What's GPA differences? Who talks to more people on the phone? Who drives faster in the car? Let's find out who drives faster in the car. So let's go here to political beliefs, and let's see who drives faster in the car. So why is that quantitative? Who brushes their teeth more? That's the real question we want to know. And the answer is there's no difference. There's no difference, no statistically significant difference between liberals and conservatives and who brushes their teeth more. But even though this difference is not statistically significant, who did we see was brushing their teeth more? On average, who brushed their teeth more? Now, it's not statistically significant, so maybe these differences are just due to random chance. Like, there is a difference because we didn't see 0 as the difference between the groups, but who brushed their teeth more on average? But the difference is probably just due to random chance. What do we see right here? Who brushed their teeth more on average? But the difference is probably just due to random chance. It's actually liberals because the... Oh, wait. No. I'm wrong. I didn't see the negative sign. Actually, it was really hard to see. You are correct. It is conservatives because it's negative, and that goes with the negative sign right there. It is conservatives. You are correct because the difference is negative. Over here on this screen, I couldn't see the minus sign, and I was like, but it's very small. It's likely by random chance. So you can see all the p-values here if we're testing for a difference. Let's go here and do some homework. So hop over to the in-between. Put on a little music right here. Which homework question do you want to do right now? Let me log into my Pearson. I turned off the computer. For some reason, YouTube's been a little odd. I'm seriously going to start looking for a new internet provider. So you watch the new internet provider be horrible. We need to get Starlink. Some Elon Musk internet. Which homework problem are you working on? Let's knock out some of the homework. Chapter 15, homework. 25 minutes of class left. We can probably do most of it, if not all of it. Okay. Let's see. Yeah, I think we'll have enough time. So let's hop over to the main screen. An organization monitors many aspects of elementary and secondary schools nationwide. Let's find that one. Here we go. The null has the what sign. Before we even look at this, the null has the what sign. I'll do a next land. You got it. The null has the what sign. The null has the what sign. Like, just put that in the chat. It's going to make this answer very easy to find. And so then we should know they're asking about what is the proportion of students with perfect attendance? That's going to be P, and the null has the equal sign, so we should see P equals to the hypothesized value. Now, this is P naught right here. And we should have, they're asking, this is the hard part of this question. This is the part people usually get wrong. It says, officials would of course be concerned if they're declining. Do these figures give evidence of a change in attendance? So you have to look for the alternative being the evidence-based claim. So do these figures give evidence of a change? So that's why we're picking, and I'm just highlighting this so you can see. Do these figures give evidence of a change? That's the alternative we're looking for. Now, of course, they'd be interested if they were going lower, but we're asking have they changed, which is does not equals. This is usually where the mistake is, because sometimes people think, well, they've gone down, so let's look for evidence they've gone down. We're going to ask, is there evidence they've changed, which is what they're asking right here. The first condition is random, which they sometimes call independence. Random and independence, basically the same thing. 10%, less than 10% of all students were sampled. We have to assume that these 8,000 plus students are less than 10% of all students. That makes sense. Now, the last condition right here is going to be NP naught and Q naught. And so we have to take this 0.36 and multiply it by 8742. And we have to ask, is this greater than what? For the success failure condition, this needs to be greater than what value? NP naught needs to be greater than what value? Because right now, P is equal to P naught. So we take P naught right here and times it by this and get NP naught, and it's greater than 10, we pass. And then we take NQ naught, and Q naught is this right here, because remember, P naught and Q naught are complements. And this is pass. Both of those are greater than or equal to 10. We are good. So now we have to find the z-score. So let's go through here and be very careful and find our z-score. Okay. So to find the z-score, which is step 2, what do we need? Let's write the equation. You ready? Let's highlight some stuff right here. I need some notation from everybody. So here's the equation: p hat minus p naught over p naught q naught over n square root. There's the things we need. And this is step 2. So what do we need right now? What do we have notation-wise right here? So we need some of the notation. What notation do we have? Let's see right here. This is the, I'll put this right here. This will give a hint for the other one. I think you might have it, Layla. Great job, Layla. No, other than the decimals, I think Layla's done it properly. Layla identified this as p hat, which is what we saw in a sample. This is the sample size right here. This is p naught is equal to that. That is p naught because p equals p naught. And then q naught is equal to this right here. So now we're going to plug in the numbers. And so, oh wait, yeah, okay, I think I have everything correct. Please tell me if I make a mistake. It's possible. And so we're going to take the hypothesized value. And then, good, I'm not blocking it. And then these are complements of each other. Great job, Layla, right there. And that's got it right there. And so we are taking the sample minus the hypothesized. And so let's go ahead and take right here, sample minus hypothesized, and then do the bottom portion. Square root, and then cool. 1.945. There we go right there. There is the z-score. Did it round up on that last one? It does. Okay. So with this right here, let's go back. Let's put in the z-score. And what if I told you, you know the p-value? What if I told you, you know the p-value? Would you believe me? I love how this one turned out. What if I told you, you know the p-value? Now, I don't want you to use the table. I'm going to put it right here. But I want you to think about this. This is basically a does not equals test. So why are we doing a does not equals test? Because of the does not equals sign, which is two-tailed. So I want you to think, I'm going to draw this for you, and I think you'll see it. So I'm going to draw this result. I'm not going to use the applet yet. So good question right there. That is the complement. Thank you, Carly, for asking. These are complements of each other, so they add up to 1. P naught and Q naught are complements. Great question, Carly. Let's throw some 20 points. So 1 minus P naught. So Q naught is 1 minus P naught. Does that make sense, Carly? Great question right there. They just add up to 1. So great. And Leo, thank you so much. Yep. Put in the chat right there. Making sure people see all that stuff right there. Now we can use the applet, but this would be a decently fair question on the test, like with a multiple choice. So I want you to look at this. And I want you to tell me what you think the p-value is close to. So I'm using the does not equals alternative, which means I shade both sides of this. So I want you to tell me a guess of what you think this p-value is equal to. And it's basically 2 right here. It's basically 2. And I want you to think about the 90 something. I don't want to say it. I want you to take a guess at this p-value. This would be a decently fair test question. I've shaded the p-value. I'll show it on the David M. Lane in a moment. Zach, you got it. I'm guessing if we put in 0.05 right here, it better like that, because that's what we're putting in. We just got it right by just being like, well, I mean, it's right next to the empirical rule, so we got it. And so what we would actually do, I mean, we can do that right there for some questions, and that's why knowing the empirical rule is important, is we need to actually take and do this. Now, look at this picture right here, and there's the exact p-value. And then I want you to look at me. Now look at you. Look at me. Now look at you. How similar is Brian's drawing right here? Brian's drawing, oh my God. Brian's drawing is what to the drawing on the screen up there? What do you think about that? Now, I know it's not perfect, but was I able to draw something pretty similar to what they are showing? And this is a great way to practice. If you have a scratch sheet of paper, try drawing out your p-value to make sure you know what it's supposed to look like, so that when you draw it, my tails were a little too fat right there, but draw it out, see if you can make the markings and kind of guesstimate it, and we can get the exact right here. And it gave it to us because we were close enough. So there's a little leeway on those. Now, we wouldn't ask you to really close exactly, so we can give a good guesstimate. On the test, a fair test question would be something like if we gave you the possible answers of like A, B, C, and D, and we said 0.05, 0.20, 0.95, 0.001. This would be a completely fair test question right here to have these options, because once you see that the P, this is basically this, you're going right for this right here. Because if you draw it out, it's very, very obvious. We wouldn't ask you to give an exact value on a test. Like the test is not going to say, give the exact p-value. But the test could ask you like, like which of these looks like they could be the p-value. And it should be pretty obvious. And sometimes we do things like the complement. This is the inside of it, and this is the outside. So we wouldn't ask you to get the exact p-value on the test. Look at the alpha level they're using. So they're using an alpha of 0.10. So this p-value is what to alpha? Higher or lower? This p-value is what to alpha? This p-value right here is higher or lower than alpha? So this p-value right here is higher or lower, because that's how we choose to reject or not reject. When the p-value is lower than alpha, which it is, we reject the null. That means there is evidence for the alternative to conclude that it has changed. So we conclude that it has changed. I think they have one last one about, is it really a big deal? This difference right here is probably not meaningful. It's quite small. So even though it is statistically significant, it does not indicate a large shift. It's a 1% difference. That's probably my least favorite part of that question, because it's just kind of it makes sense. They want you to interpret it. In this case, would you reject or fail to reject the null hypothesis since it rounded to 0.05? If it was exact, like if they used an alpha of 0.10, then we would need to get, like if they used an alpha of 0.05, then here we would not reject the null. Correct. If the alpha was 0.05, we would not reject the null. Does that make sense here, Layla? If the alpha was 0.05, we would not reject the null because that's above 0.05. And if it was exactly 0.05, like if we had an instance like this, and I'll never make a question like this, I would not like this, but statisticians would say you would not reject the null at an alpha of 0.05. We only reject the null when it's lower than alpha. So if your alpha was 0.05 and this was your p-value, you would not reject the null because you have to get a p-value lower than alpha. So if it's exactly on alpha, you don't reject the null. And I will never write a test question where it's exactly on alpha. It wouldn't be unfair, but I don't know. I don't like that. We have advanced ways of dealing with stuff like that, which that's why I'm like, yeah, there's ways of dealing with that. The next one was, I think someone put another question they really wanted in the chat, and then we'll do that. A governor is concerned about his. I think it's this one. It's this one right here. Okay. A mayor is concerned about his positives because they changed the wording on it. That a city job performance, let P be the proportion of residents who express approval. The null has the what sign. The null has the what sign. Every time we do a null, the null has the what sign. Got the hiccups. The null has the what sign. Every time you see a null, you're like, that null has the what sign. And they want to see, let's look at the alternative. He wants to keep his positives above 76%. Oh, I need to scroll down. The equal same is just going crazy there with those equal signs. The null has the equal sign, and they want their positives to be greater than that right there. Is a 20-sided dice fair? The null has the equal sign. Love these questions, right? And then we're asking, is it fair? It's either fair or it's not fair. And if it's not fair, then it won't roll the side we're looking at 1/20th of the time. So this would be not equal because it's either fair or not fair. It either roll it too much or too little. So that's not equal to it. Either rolls it 20% or 5% of the time because that's 1/20th, or it does not roll it 5% of the time. Does that make sense? Great job, Layla. Excellent work. Only 29% of people who try to be more assertive succeed. Sellers of a motivational tape claim that listening to the recorded message can help people succeed. So they're trying to help people be more motivated. So they're claiming that the true proportion of people who will be motivated is what to 29%? Well, we know the null has the equal. So they're claiming the true proportion of people who will be motivated to will be more assertive is greater than that hypothesized value. And that might be it for it. That's got it. This is talking about a p-value, and this is a good one just to see the p-value interpretation. We'll go back to it right here. But the p-value is the probability, which it shows right here, is the probability of getting your result via natural sampling variation or a result as extreme in it would occur 52% of the time, given that there is no real change. So this last part is given that the null is true. If there really is no change, that's the null being true. We're assuming there is no change, and then we're looking at 37 point, yeah, exactly. So this is the null value. 37.7% of the time, we would see as result as extreme or more extreme than 52, given the null is true. So this right here is a pretty good interpretation of a p-value. I like to word mine a little bit differently. To see how I would word a p-value interpretation, we could say this right here. The observed results of 67 inches for our sample of UT students would occur basically never, given the truth for UT students is 6 feet 6 inches. Like if we went out and take a sample and the truth is 6 foot 6 inches, we would basically never see, this is the probability of seeing what we saw, we'd basically never see something as extreme or more extreme than this, which we're looking at that does not equals. So I would say that the result we saw in our sample of 50, or not, that's not the sample, there it is. The result we saw in our sample of 67 inches tall would basically never occur. There's the p-value, never occur, given 66 inches, 6 foot 6 is true. We would basically never see that result. One last one on the homework right here. Aha, let's do the last homework problem. And I think we have time for one quiz, Layla. We can do that right here, end the video if you have one quiz one you want to do, and then we'll come back to some more on office hours. In a 1997, can we do the one on the quiz that says write out the null alternative you can use to test each? Yeah, let's do that right here. Let's finish this. We'll do that. We'll make sure we do that one because sometimes we go a little bit over on class, and we'll come back. We'll do it during class today, so we'll do it right after this, Layla. So we'll finish off the quiz. This one right here is another proportion test, and let's take a look at it. So I'll solve this one. Remember, what do? We start by marking our notation, and it says reports indicate that 2.1% of hospital births are twins, and we see 7 sets of twins out of 529 teenage mothers. So this is going to be X right here, and this is going to be N, and this is the hypothesized proportion. So we need to test. Can anyone find for me p hat right now? Can anyone find p hat? What is p hat? And p naught is equal to 0.021. What is p hat? P hat is going to be x over n equals p hat. That's 7 over 529. That is what we saw in the sample. Great job right there, Layla. Excellent work. That sounds like the right answer to me. I'm just going to make sure we got all the decimals carried. 7 divided by... Cool, we got some more decimals. Okay, so then we're going to take, and let's do this right here. P naught times Q naught. I'll write it out so we can see it. So square root P naught times Q naught. Go. And we'll abbreviate this for the moment. I'm going to carry all decimals when solving this. I think, whoa. Oh, no, it's not that below. Carry all decimals when solving this. If you get it off by a decimal because you don't, let me know, but just carry all decimals. P naught times Q naught over N square root. There we go. There's that. And gotta make that a little clearer that we're dividing by that. That looks to be about right. So then we go 7 divided by 529 minus 0.021 divided by this. There we go right there. I see. So I'm getting this right here, Layla. This might be because of the decimal carrying, because there's a lot of small decimals going on in the background. But I'm getting negative 1.25. And that might be the decimal carrying in the background. So let's see. Hopefully, fingers crossed. So are all the conditions met? Random, 10%, success, failure. And the null has the equal sign. And we're seeing Is this the same? So what alternative should we pick? Because we're seeing the null has the equal sign, so we can't eliminate with that. But which should we do right here? Which should we do? We're saying, is it the same for young mothers? So we're asking, is it the same? So which alternative? It is A. Great job right there. It is A. And so we just calculated the z-score, and it says to 2 decimals. Good job. It might, I don't know if it would have, make sure, can I change it? I can't change it. Make sure to carry all the decimals. Don't round till final answers at the end. Carry all decimals in the calculator because it can get pretty iffy. I can maybe guess the p-value here. I can maybe guess it. Oh, no. It's asking, is it the same, right? That should be close to it. Really? Okay. Let's go get the actual p-value on the David M. Lane applet. We need to put in the z-score. And we're asking if it's the same. Oh, it's a 20% confidence interval, isn't it? Oh, there it is. 21. There it is right there. I reversed my confidence intervals. Don't worry, I'm saying confidence intervals because I'm doing something else. Round to 3 decimals. I was taking a guess at it, and I used the wrong number in my head. So there it is right there. I was just trying to do it in my head. That is the right answer. And that's why we should use the applets to find the answers. So make sure to use the applet. So there's the David M. Lane applet. And I was trying to do it in my head. And yeah, that's why I failed. Now I put it into the applet and we get the right answer. So do it in the applet. Now, what do you think we're going to do right here? The p-value is high. So what are we going to do? Reject or fail to reject the null? What do you think? The p-value is high, so reject or fail to reject the null. The p-value here is high, so reject or fail to reject the null. A, B, C, or D. The p-value is super high. When the p-value is high, just let the null fly. Fail to reject. That means we don't have evidence for the alternative. And that's got it. 100 on the homework. Excellent work. Let's go here and get that last homework, or get the quiz question. You said, I think we got just enough time. Let's go find that quiz question. A little bit of music right here. Chapter 15, quiz question. Got just enough time before break right here. I did preview. Replace questions. And let's go take a look. And you said, can we do one quiz that says write out the null alternative you would use for each situation? Okay. Ah, here we go. So is this the one right here, Layla? Is this the question you're wondering about? Was it, I think this is it. Okay. Because this one's a little bit different. This one has multiple blanks. What can we automatically do for the null? What can we automatically do for the null? I'm just going to go here for every single null hypothesis and just put this in. And this goes to today's lecture, where we were talking about writing the null and alternative. Go all the way back up here to the start. When we talk about writing the null and alternative, the null always has the this. The null always has the this. Always has the equal sign. Then we need to find the parameter we're going to use. So the null has the equal sign for all of these. These are different questions, but we're just going to put the null has the equal sign. Don't be tricked by those. Now we need to know what parameter we're using. In 1950, only about 40% of people went to college. So we'd have to ask someone, did you go to college? So which one of these is the did you go to college question? Is it the true mean, the sample proportion, the true proportion, or the sample mean? Which of these would be, we're asking, did you go to college? And we want to find out the truth for did people go to college? So you can look at this right here. Kind of got a hint. It's P. Because we're testing the true proportion of people who went to college. That means this is here and this is here. Now we're asking, has the percentage changed? So since we're asking, has it changed, we only have to choose from less than, greater than, or does not equal to. Don't be tricked by the other signs. Less than, greater than, or does not equal to. We're asking, has it changed? So asking, has it changed, would that be less than, greater than, or does not equal to for the question? And it was proportion because we're asking, did you go to college, which is a yes-no question, which is categorical. And we would choose not equal to, not equal to. This one says 20% of cars of a certain model, great job, Layla, right there, have needed costly transmission repair. A manufacturer hopes that the redesign of a transmission can help solve this problem. So are we asking the mean of transmission problems for cars or the proportion of cars that have transmission problem? Which one of these are we looking at right here? Is it mean? And the only answers could be P or mu. Those are the only two answers we could do right here because that's for categorical and this is for quantitative. So is this question about cars needing transmission repairs, which is a yes, no question. Did your car need transmission repairs? Is that proportions or is that quantitative? It'd be proportions because we're asking, did your car need transmission repairs? When you collect data, you'd say, did that car need transmission repairs? And that means P goes right here. And because the only thing that changes is the sign. And then the manufacturer hopes a redesign will help solve this problem. So this one might be a little confusing, but we're going to say less than because they're trying to lower the cars. Like the true proportion of cars that need transmission repairs is less than this. They're hoping to show evidence that they can make it lower. Next, we see we test out a flavor of soft drink. Is it ever going to do mu? They're trying to trick us here because we want to ask if people like this flavor, and that's going to be the null value right here. And so we want to see over 60% of people like the flavor. That's what we're asking. And we have to ask people, do you like the soda flavor? Do you like the soda? And that's proportions again. They were trying to trick us right there. Just no mu. Mu would have to be, I think you can get mu on here. Can you eventually get mu? Really? Well, that's a bummer if it never gives you mu. It does different versions. Well, maybe not. Isn't there another version of that problem? Bunch of problems with proportion on here. Should do more ones on the mean. So much proportion testing. We'll see more with the means, though, as class goes on. But yeah, lots of proportion. Any last questions as we head off right here? Quantitative. I think the next chapter has some quantitative stuff. Yep, it does. No, it does. I can see it. More quantitative coming up. Mine was like yours, so I don't think I don't think so. I guess there's not. Some of the questions have way different versions. Sometimes they'll change it like from semester to semester. Like my Pearson controls the questions. And so they just have it on their site. But I think that's got it. Let's head to space. Hopefully people are getting some good work done on the assignments. We'll hop back here to office hours in a little bit. Gonna go grab some food. But great work. Keep working on the assignments. Keep asking those questions. Only 3 more days left after today. Oh my gosh. This is it. The last 20% of class. You got this. Keep working hard. I'll see everyone soon. Office hours coming up soon. Bye for now, everyone. Bye. You bet. We'll talk about the office. We'll talk about the project during office hours. You got it, Layla. Swing by office hours, project talk, and assignment talk. See everyone soon.